workshop. Bear with me a second. Sorry about that, my printer deciding to boot up. So once again, welcome to our presentations this morning. And so we're going to start with Anna Grat from SGS, who's going to talk to us about laboratory procedures. Just before we get there, remember everybody, you can see the CVs of your speakers in the pack that has been put on the chat. So let me stop sharing. Okay, Anna Grat, if you can share your presentation. Thank you very much.
Thank you very much, Tanya. And thank you for the invitation to be part of this again this year. Just a quick welcome from my side. I work from SGS. I'm a geologist by trade. We're specializing in mineralogy, and for the last 2 years, I've also been working with our Geochem team to actually build laboratories on client sites. So that is where I come from, and I would love to share some inside info with you guys as to how you can actually use laboratory procedures and make it work for you, because I know sometimes it is a bit of a pain to get there. Okay, next slide. Just to give you a little bit of background of the company that I work with. SGS is a global company. We have about 89,000 people that work for us across 11 industries. And we have a network of over 2,600 offices and laboratories across the world. So chances are that wherever your project is, there might be a SGS office. And even if it's not minerals, we do offer logistical services through our other industries. On the mining side, we do offer all our customers across the whole mining life cycle some services. So this value chain, this will go from exploration up to your trade stage, and we will offer you different services in each of these categories. Just to show you where we are, beginning of this year, we've changed our footprint a little bit, and we're calling ourselves Natural Resources now, of which our minerals department is one of our natural resource offering. In this, we have about 440 labs in 130 countries, specifically for on-site commercial, multi-labs and professional offices in the mining industry. So minerals in South Africa, where we are sitting at the moment. Minerals don't just include the geochemistry, but also some other disciplines. So we have commercial labs and on-site laboratories for geochemistry. We have a mineralogy facility that currently has a brand new, you guys would have known it as QuemScan work, where we look at mineralogy. Well, the new instruments are made by TechScan and they're called the Tima X. They offer a higher resolution on your imaging, as well as better assays on your material. So that is something new that we have at mineralogy. We offer metallurgical test work. We do energy minerals, which is our coal. And there we have commercial laboratories as well as on-site and trade. And then we also have a section called non-energy trade. And they look at any other commodity that you want to export, where they actually prepare a export certificate for you, on which you can get paid for your commodity that you're selling. So now specifically Geochem in Southern Africa and South Africa. On the commercial side, you'll see we have laboratories across the country that can assist. Because gold is so big in South Africa, our Randfontein laboratory does a lot of gold, but they're also our hub of excellence. And you can do any of the geochemical analyses at Randfontein. Vaal River Laboratory is also gold oriented for more the Wits gold, and then Barberton Laboratory for the Barberton gold. Rustenburg is for platinum and chrome, and the Katu Laboratory is actually an on-site laboratory that is basically a hybrid, so they can take in work from other clients as well, and they focus on manganese and iron, and all of these laboratories are accredited. What is an on-site laboratory, you would now ask? Well, for an on-site laboratory, we basically do full laboratory analysis for clients at the site itself. So in these on-site laboratories, we use exactly the same equipment and quality procedures as we would in a commercial laboratory. The only thing is we need enough samples to actually make it worthwhile for the client to have this on-site. And then we see that most of our on-site laboratories are at facilities that produce a lot of samples, or are in very it's very difficult to get to the places. So it's maybe something in the Congo where we don't have a big laboratory close by, so we can put up something on the client side to make it easier for them to get their analyses in time so that they can make decisions. Then something that I'm actually working on is the field analytical services and testing. So this is actually the first stage of having something on site on a geochem basis, and we also put in a little bit of mineralogy in there. This is where you have a site where you're producing a lot of samples. You need to send it to a laboratory, but it's very expensive to actually send it to the laboratory, these big samples. So what we can then offer you is a sample preparation unit, and it's a mobile little unit, and it's containerized. And we can then prepare, the smallest one prepares about 150 samples per shift. And what you can then do is just reduce the size of your sample to get a representative small sample that you can send out to a laboratory. In this, we can actually put some other stuff as well to make your life a little bit easier. If you are at a drilling site, we can put in some continuous X-ray fluorescence scanners that can actually map out your drill cores chemically. We can put in PXRF, and that's those handheld systems or the desktop systems. I hate the point and shoot method. We don't do point and shoot with this. This is a calibrated setup on a powdered sample or a pulverized sample, so that you get usable results from it to actually direct your drilling. In addition to this, we can put on some mineralogy tools as well. For bauxite projects, it is very nice to have an FTIR on site, as you can look at your available alumina and silica with the FTIR. We can add PXRF, XRD or XRDs to things like smelter laboratories or smaller projects where we're looking for one element or one mineral specifically, and we can set up an automated system to do that. And then you also have a near infrared, which is hyperspectral scanning that can be done with either a small unit or a big unit on your site. And this is great for drilling programs or even for plant control. Okay, so now we get to the fun stuff, the analytical processes. So just to give you an idea, what is an assay. So any chemical analysis that determines either the portion of metallic elements or non-metallic elements that you have in a sample is commonly referred to as an assay. So there's a wide variety of geological materials that we can chemically analyze. And we even test for water, vegetation, and then the geological materials more like soil, sediments, and rocks that we can look at. And the assay labs can then provide you with a single or a multi-element analysis, depending on what you're going to do with the data. So there's a variety of methods that we actually use to do these analyses. And I'm just going to quickly go through them, give you an idea of what we're looking at. Firstly, we have sample preparation, and we'll look at what steps actually go into that. Then we have a section in our analytical guide that says miscellaneous analyses. So these include things like SGs and moisture and small things that you sometimes need. And the big ones are fire assay, which is usually used for precious metals, your X-ray fluorescence analysis or XRF, which gives you modal analyses. So it's your bulk minerals and your majors. Inductively coupled plasma, It can be either optical emission or atomic emission, which again, it's the more abundant elements that we look at. And then the ICP with the mass spectrometry, which gives you your trace elements. Then there's a couple of others that we're not going to focus too much on today. Atomic absorption spectroscopy that you can also use for things like for fire assay finish. Wet chemistry, where we look at single elements with usually it's titration methods. IR combustion methods, where we look at sulfur and carbon. Then we're going to talk a little bit about QA/QC and how your quality control actually works, what goes into quality control. And we are definitely going to discuss detection limits so that you understand why the lab always asks you for what you think is in the sample. Okay, so sampling. To me, this is the most important part of your project. The objective of the sampling obviously is to get the most representative sample in the most unbiased method that you can get. You're never going to get a perfect sample, but you have to be happy with that sample and that it is acceptable and affordable, and it's got a good degree of precision. So the types of sampling that you guys are going to encounter, and I think you might have already had a talk on how to sample. We have lots of core drilling samples coming in, reverse circulation drilling, auger drilling. There's a bunch of other drillings like sonic drilling methods that you can also use, channel sampling, trench sampling, geochemical and environmental sampling, water samples, run of mine, or feeds, crusher product samplings, etc., etc. The main aim of this is to get a representative sample. I always say, remember, if your sampling is bad, garbage in, garbage out. So if you've got a bad sample, then your results are also going to be bad. If you've got a good representative sample, you'll actually get good results from it. Okay, then now you've got a sample. Now you want to send it to the lab. They're going to ask you a bunch of questions before you can actually submit your sample. And this is all for them to have an idea of what they're working with and to give you advice on what to do with the sample then. So they're going to ask you the sample type, and you can then actually just tell them what it is, whether it's a core sample, rock sample, chips, sediment, soils. Is it a concentrate that you're putting in, a metal? Is it something else like a vegetation sample? They need to know that, because that would influence how they will prepare the sample, because in the sample prep that we're going to discuss just now, again, you have to have a method that brings down the mass of that sample to a mass that you can work with on the instruments, and you have to still have a representative sample. So they need to know how many steps they have to put into the sample prep to get to that representative sample. They also need to know the mass of the sample, as that also influences how they're going to prep it. Then you have to tell them how many samples you would like to submit. Usually in big batches, there would be some discount applied, because it's easier to prep a lot of samples that have the same prep than just one. We would like to know which commodity you're working on, or specific elements of interest. And this is where the analysis grade now comes in. They want to know if it's an exploration sample, if it's part of your ore body. Is it a control sample from the plant? Is it a third-party sample or umpire sample that you're sending in? This is so that they can recommend the correct method for the analysis. Because when we get to the analyses, I will show you that different, those like exploration samples have different detection limits from ore grade samples. And this is just so that the methods are set up for a specific detection limit, so that we know that we get the best results for each analysis. You also please need to let the lab know whether you've got hazardous materials. This includes our norm samples, which is naturally occurring radioactive material. Things like uranium, or some of the Wits gold, for example, is very radioactive, so you need to let the lab know. Also something like asbestos, because obviously we have some special precautions that we have to take when we have to work with these types of materials. Okay, now you're going to submit your sample. Firstly, once you've given the information, the lab will then supply you with the quotation, and they will attach to that quotation a sample submission form. This is where you give your company's information and contact information and most of the sample information afterwards to just say, to confirm everything. Please make sure that your samples are neatly packed and clearly marked. When they go into laboratory, they will be logged. And if the sample numbers are a mess, then sometimes there might be issues coming into the lab and logging those samples. If you've got 2 samples with the same number, for example. Please also submit a hard copy list with the samples just to make sure that they do have the right list, and then a digital sample list with the submission. The lab will then either supply you with a pro forma invoice, or you can use the quote to then give them a purchase order, or if you don't have an account, a proof of payment. And then once you've got that done, then things can start happening. As soon as the analyses are then completed, you will receive a report and the project invoice. So I know project admin can be a big pain. I remember when I was still working in mineralogy and had to like fill in all the stuff every time I submitted samples. But if the sample admin is not in place, it really leads to some misunderstandings and delays of the analysis. So if you follow the proper procurement process, then the turnaround time of your samples will be as it is stated in the proposal. Okay, so now we get to this, your sample is submitted to the lab. Now what happens next? This is where we start with our sample preparation. And the different steps will vary according to what you're actually submitting. So firstly, your samples will go into the sample receiving area, where they will be logged on a laboratory information system, or LIMS, so that you can track your sample straight through the whole process. For this, the sample is then weighed and the weight's recorded. And then different things can happen to your sample depending what it is. Say if we're looking at just normal rock samples, they're about 10 centimeters big in size. So we will make sure that the sample is nice and dry. If it's very wet, sometimes we even have to do some filtering to get them dry. Then they will go into different stages of crushing until we get to a product that is about 70% passing 2 millimeters. We will split off a certain amount of the sample, usually about 1 kilogram, and that will then go into pulverizing. We will pulverize to 85% minus 75 microns, which is the normal pulp size for most of our analytical technique. Other things can happen. There could be some screening analyses being done. Sometimes we have to composite some samples for clients, and this can be done either before we start the process or with the pulps. We do bulk preparation as well. We've got a huge plant, it's amazing to see, where they have samples in bins that come from the mines, massive samples. It's tons and tons of samples that go through a massive crusher. It goes through multiple crushers actually, and it's conveyor belts that run until they split off samples for the assays. The rest of the sample, once you've got the pulp, whatever's left goes into storage, and it will go either back to yourselves if you request it to be returned, or it will be disposed within 90 days of the analyses. Okay, now looking at the different types of analysis that you can get. So there's lots of miscellaneous things where we can do a small acid wash, to make composite samples, some moisture analysis with different techniques. We can do loss and ignition, which we can do on a gravimetric method where we use furnaces, or we can do it on a TGA, the type of machine that does the heating, and that can be done at different temperatures. You can have specific gravity with manometers or volumetric. Bulk densities, where we can do wax immersions or non-waxed immersions, depending on what your sample looks like. Particle size analysis with sieves or with laser diffraction for the smaller, finer materials. So there's a bunch of these little things that sometimes is of worth, like bulk density, to actually know if gravity separation, for example, going to work. And there's complementary methods that the mineralogy and the metallurgy team do to complement these miscellaneous analyses. Okay, so now we get to the one that we all know and love so much, gold. We do our precious metals mostly by fire assay. So now we're going to start chatting about the detection method, detection limits, lower and upper detection limits. If we look at gold and we look at exploration grade gold, there's different methods that you can use, and that's really all up to what material you have and what you actually want to know. So for exploration, we do offer a fire assay, and it will have an AAS or ICP finish. So it means we actually do the fire assay, you get a prill, the prill gets dissolved, and we then check the gold value with the AAS or the OES. And we use about 30 to 50 grams of material for that. So this is where you can see that we actually need to get a good sample in and have a good preparation to make sure that we have a representative sample. Things that are important in gold is if we will look, sometimes when we see free gold or bigger pieces of gold, then you actually have a problem with your assays. Because if you've got a huge piece of gold in a very small sample, you might miss it with the sampling. That is when we look at things like blegs, where we can actually put the sample in, and it's a bigger sample that goes in, and we can then with the cyanide try to leach the gold out and check how much is in there. So it's very important to tell us where the gold comes from so that we have an idea of what we're looking at, and then choosing the right method for it. So exploration grade, you think there's gold, not really sure, you don't know if you've hit the gold veins, for example, then we'll look at exploration grade. So here we will look at lower things. So we'll go from, for example, from PPB level up to PPM level, just to make sure that we catch the gold. If we know that we're in the ore zone, we look at ore grade. Then we're going to look at PPM level and a little bit higher. So this gives you an idea about the detection limits. So if you give enough information, we can test the right thing. What happens often is people don't tell us, then you go in with an ore grade analysis because those are the more stable ones. You can imagine the lower you go down in the detection limit, the bigger you can have bigger problems there because there's a bigger gap with the detection limits and the reproducibility and consistency and accuracy with very low detection limits. So somebody would say, no, I definitely have gold. We put it in at an ore grade and we find nothing. Then we have to do a second assay to actually get the low detection limit to find out if we do have gold. So the more information you give, I'm going to say this still a million times, is very important at the lab. We also offer screen metallics. This is where they take about a kilogram sample, they screen it into specific size fractions, and then they do assays on the different size fractions. That actually gives you an idea of where your gold is grain size wise, where it's sitting. And then we have control and concentrate grade samples, which is then go from ppm levels to high percentage level. We do that. Unfortunately, we do not do trade analysis for gold. So usually in every country in Africa, trade analysis are done by government laboratories. We can do the purity levels, but you cannot use it for trade. So that's just one thing to keep in mind. I get a million emails in a week just to ask, can you please check the purity of our gold for trade? That is just part of the system in African countries. A third party cannot check it. It has to go through a government institution. Then we get to PGEs in gold. We can offer you that as well. Same thing. Most of you will know the term fire assay 6E or PGEs. That is something that's very unique to South Africa. Nobody else does that across the world. But that's a nickel sulfide collection method where we get the platinum minerals with that, and then we do the gold part with our normal lead collection method for fire assay. Again, give us as much information as possible on your PGEs so that we know which method to actually give you. As you know, the PGEs are in any case very low, so most of our methods will have an ICP finish just to check for those PGEs because they are very, very low and they're still viable. Okay, exploration grade analyses. Okay, this is where you're going out to the field, you've got your drill rig going or your trench sampling going, and you want to know what's in your sample. So the detection limits in exploration grade, like I said, for the gold are lower as we are expecting lower concentrations of the elements of interest. So also look for path-finder elements at this stage, and this is why we do the elements specific to what you're looking for. For example, we'll look specifically, say, with a XRF method, maybe for some copper, because copper works really well on XRF. But then we'll do a fusion or a digestion method for ICP to look at multi-elements that you're looking for. I know a lot of people love 4-acid digest. But just to give you an idea, if you do a 2-acid digest or aqua regia digestion, it's a very weak digestion, so you only have partial results for some of the elements because they don't completely dissolve in those acids. If you're looking at 4-acid digestion, you already have a bit of a better digest, but refractory minerals such as oxides have very limited solubility in the multi-acids even. And then also a lot of minerals often precipitate or volatilize during the digestion method, so you lose them as well. I actually prefer using the fusion method, the peroxide fusion, or a lithium metaborate fusion. The peroxide fusion you use for refractory minerals because they are soluble, and the temperature of the fusion is low enough so that the hydride elements do not volatilize. On the lithium metaborate, which is the same fusion method that we used for XRF, it is a high temperature fusion method, so it does dissolve the rock forming minerals as well. And you also get the trace minerals and refractory minerals. So that's two good options for multi-element analysis if you want to look at that. Generally for XRF on the exploration side, we just do loose powders or pressed pellets. That's what's recommended, but I would still do a lithium metaborate fusion XRF just to get my majors. To give you an idea, on the XRF, we'll just get all the majors and then you just do your sodium or the lithium metaborate fusion on your ICP to get the traces. Then we also have mobile metal iron, or what we call MMI. It's a trademark SGS service. This is where we use very weak extraction on mobile ions for regional exploration projects. I can give you more information on that if you're interested on that. It works very well for things like gold, and you use soils with weak extraction to actually do these analyses on. We are set up for a few other methods, but if you are interested in that, I can just pop me an email and I'll give you more information on that. Okay, so this is for exploration purposes. This just gives you an idea of what's going on. Then we have a second category called ore grade analysis. So this is for mine grade control. This is when we know that we're busy working with our ore. Again, we have digestion methods and XRF methods and fusion methods. So on this side, we are looking now at our ore minerals. ICP will then have the lower detection limit will be moved up, and the upper detection limit will also be moved up, because now we're working with something that's a little bit more easy to get. Please always remember, if you're looking for silica, SiO2, and you're doing only ICP, it will not be accurate. You never dissolve all the silica in a digestion. XRF borate fusion works brilliantly for silica. Weirdly, even the silica on the fusion methods at the ICP is not great. So if you need to have silica, if you say you're doing XRD, work on this as well to see what minerals you have. And it is quantitative XRDs that are validated against the chemistry. Make sure that you give them an XRF borate fusion analysis, because the data is just much more accurate. So again, use your XRF for your majors and use your ICP methods depending on what you're looking for. You can choose a digestion or a fusion method. Again, I prefer the fusion methods as a geologist. I just feel they give me better results than the digestion methods. But you will find that, and I'm getting into that category, older geologists do prefer that for acid digest, but try it out. Send the same sample and see what you get for acid digest, see what you get out of fusion and how it compares. To me, the fusion just gives me better results. Then we get to control grade analysis. Now, what control grade analysis is, it is actually where you're starting to have upgraded samples. So this is something that goes through the plant, and now I have different things to do with it. In some instances, it will still be solids, like after we've had a flotation, you still have your floated minerals will still be solid that was sludge that you can look at, but we also have solutions. For example, if you're looking at gold running through a cyanide leach, you'll actually have a liquor that needs analysis. So this is where the solution part comes in for ICP and titration methods. Again, you can use your borate fusion for your whole rock analysis. There's also AAS methods and ICP methods for whole rock. And then again, your ICP methods for, and usually these are digestions again, to look at specific minerals that you're looking for in these control grade samples. And just a quick word on trade samples. I know many of you will get into the position where you have to work with trade samples at some or other point. This is usually a plant product or a smelter product that needs to be now sold. So this has the highest lower and upper detection limits of all the methods. And there can even be, it just depends. It could be a metal, it could be just a concentrate. And this is usually done in triplicate. The analysis method will be chosen based on the commodity that you're looking at and the type of sample that you're submitting. Usually these certificates of composition is issued and then used by the buyer to pay for the shipment that you're shipping to them. The trade analysis also looks at any penalty elements that may be in your sample that might bring down the price of your sample if we're not within those limits. So if you ever do any trade minerals, you will see that there is specific sampling methods for getting the samples, and then everything is done in triplicate. And we look at certain, and you supply the trade team with what your say limits are for penalty elements. If you look at something like iron ore, they definitely look at silica, manganese, magnesium, calcium, phosphorus, barium, sulfur, things like that. It just depends on the buyer and what they actually need. And those limits will also be determined by what they want to do with the sample afterwards. So if you don't fall into that category, sometimes what I see a lot at the manganese mines where we work a lot is they actually blend higher and lower grade material to get to that product that actually falls within the limits that the buyer wants. So it's important to give them the trade team also all the information on what your buyer is actually expecting from the material that you are analyzing. So on the trade side, again, if you need more information on this, please contact me. I'm not a specialist on trade, but I can put you in contact with somebody that actually knows more about it. But like I said, this is the analysis that has to be perfect because you're actually getting paid on it. Okay, so Then to make life a little bit easy for us geologists, some of the laboratories do offer commodity packages. And these are packages where the analyses are actually tailor-made for that specific commodity to make it easier for you. So rare earth elements, iron ore, bauxite, nickel laterites, manganese, chrome, uranium, lithium, fluorspar, graphitic carbon, base metals. These are just some of the packages that you can find, and then you can choose which analysis packages would suit your ore. Just on the accreditation side, now that we're with commodity packages, in the past, you could actually accredit a method like XRF. This changed a few years ago. So often you will see at the laboratories, they'll have a accredited XRF method for iron ore, but the bauxite isn't accredited. And it's exactly the same method that they're using, but unfortunately, SAMESC has changed that accreditation to be for a specific commodity rather just than for a method. Okay, so just because a method is not accredited does not mean that you're getting a bad or a less useful assay. Everything is still run, for example, at XRF with exactly the same method and the same quality procedures to make sure that you get the best result. Sometimes it's very expensive to do an accreditation on a specific commodity. So you can think if in the past we had XRF, so all our XRF analyses were accredited. Now we have to do it per commodity. So it makes a huge impact on your bottom line. So we tend to only accredit methods where we know that we get a lot of samples in. That's why you'll sometimes see something is not accredited because there's just not enough samples coming through the lab to actually warrant spending so much money on accreditation. But still, we're using exactly the same method that's used on the accredited methods and the non-accredited methods. Okay, then QA/QC. QA/QC is very important to us because this makes or breaks a laboratory. We have to make sure that the results that we give to you, the client, are the real thing and that there's nothing dodgy or fishy about it. So in our QA/QC program, I have a whole long document that explains everything. But basically, the main things that you use in QA/QC is to do duplicate analysis and then check those duplicates against each other to make sure that you're in the same, within a tolerance in the same ballpark. Because no two samples will be exactly the same. But if you have two splits of the same representative samples, they have to be within a tolerance of each other when you analyze them. Then we also do blanks, and often clients will also in big sets of data, you will submit duplicate samples. You don't tell us where the duplicates or the blanks are, and we just analyze it. And then you can actually on your side check that you're happy with what we're doing. We also run certified reference materials, and these are chosen based on what we're looking at. So if it's the CRM for the exploration samples will match the detection limits of exploration samples. Something for a plant product will match the limits for the plant products, so that we make sure that that CRM passes our inspections, and that they match up with what we have as the certified method, or the certified oh, my brain is broken today. It must just match up. So if I have 10% copper in my certified reference material, then I have to have 10% in my assay of that certified material. Then we also do a lot of round robin analysis, and this is usually done between different companies or different laboratories. We like running round robins because that also tells us how well how well our analyses are. So, for example, we have an internal round robin in Katu at our UMK laboratory, where we are actually running the same sample between us and all the on-site laboratories of other companies in the area. And that gives us a good idea about where we stand on how good our analyses are. So we like doing that. And we're also entering into a few new round robins this year. So that's one of the ways that we do our QA/QC. All our results are also checked before they go out to make sure that everything on that list is checked. But you are very welcome to always add some duplicates and blanks to the samples that you're submitting. We won't know where they are, so that will give you a good idea of what we can do and how good the quality control actually is. So that's basically all from me. I hope you've learned something today, just to give you a better idea of what's going on in the lab. I know it's daunting. When I started working with the Geochem team, I was completely confused. But it's easier if you know that why they need to know what they need to know. So any questions from anyone?
Anna, great. We've got a large number of questions in the chat box.
Okay.
Okay, so the first question is from Leilani. Would energy minerals also include those used to produce components and materials needed for green energy, such as neodymium, or only minerals directly producing energy?
Unfortunately, energy minerals at the moment is only coal, but HGS is busy. We've started a program called Sustainability. And that is where we're starting. I think they started in Europe to looking at things like neodymium and then other sustainable types of energy. And that will be rolled out across the group very soon. So I can, if she sends me an email, I can send her a little bit more information on that sustainability side. So that's going to fall under sustainability. That's also going to include electronic scrap and things to recycle that. So that is something that we started working on about 2 years ago, and that should be rolled out.
Thank you. Then how do you avoid contamination on such a huge scale processing? Cleaning generally takes very long. How does one do it effectively at such a scale?
So we have very strict rules about cleaning. So that's also, we won't be prepping, say copper samples and gold samples at the same time and the same machine. So, and in between every process, for example, in a crusher, there will be non-contaminated silica going through between every crush. Same with our milling pots. Yes, it takes a lot of time, but it's absolutely worth it just to not contaminate. For example, if you're working with carbons and graphites, we actually have a separate set of equipment. We have a prep section just for that because we know how easily that can contaminate our other samples. There's a specific area for gold preparation and then for general preparation. So yes, cleaning takes a lot of time, but it's something that you just have to do. So we actually factor it in our timing and our turnaround times.
Okay, next one. Standard reference materials are difficult for coal using XRF as the standards oxidize and degrade. What is your recommendation for trace elements in coal analysis?
I will have to ask you to mail me so that I can actually ask the coal guys. I don't work with them that often. I don't have a lot of experience in coal, so I have no answer for you at the moment, but if you can pop me an email, then I can actually put you in contact with somebody that can help you on that.
Thanks. Nadira, if you will then follow up on that, send an email.
I will do. Let me go to the next slide, then you can get my email address at least. Yes, there we go.
There's also a question regarding sharing your QA/QC document. Would you be available to do that?
Yes, I will be able to do that for you.
Okay, you can either pop it on the chat or send it to the GSSA and we'll send it out.
Okay.
Then Carrie's asking a question. Could you give us insight as to how age of the sample that is between extraction and submission to the lab might affect laboratory testing?
Oh, that's a good one. We do find that sometimes if you have something that degrades very fast, you will have problems. So you'll have to package it even some people actually package things vacuum sealed to make sure that there's no air on their sample to degrade it. What we find often is, especially on dump sites where they are reprocessing dumps, we find that the original assays compared to our assays with all the degradation of the samples do give you a very different result. So if you know that you have a very sensitive sample, make sure to pack it so that you, when you send it to the sample, to the laboratory, so that you have minimum degradation. We found with like copper samples sometimes that's an issue where they're wet. Sometimes you actually dissolve stuff. So dried and vacuum sealed sometimes is the best way to go. But luckily for most deposits, that's not really a problem. It's very, I think potash and things like that, that can be a big problem.
Then we've got one regarding PGEs.
Yes.
Using a lead collection method and an OES finish,
Yes.
how do we know how homogenized the lead button is?
Remember that lead button is then dissolved. And then we do the ICP finish on this fluid, on the liquor. So ICP is all liquids. So anything that you put through ICP, if it's not a fusion method, so for platinum it will be a liquid. Yes, you're actually dissolving it into a liquor and then putting the liquor through the ICP.
Okay, and then last question, or second to last. After COVID, Lauren wants to know if lab visits can be organized for graduates and so forth.
Definitely, definitely. At the moment, we are at some of our laboratories, we don't allow people, but like at Randfontein Laboratory, we already allow visits, but unfortunately not for big groups. But after COVID, anytime, you're very welcome. And the same goes for mineralogy, metallurgy, or whatever you need to see. We'll be very happy to see you there.
Just one very last comment from Paul. Paul, this Geoskills presentation is about what geologists need to know. What you're talking about material inspection and testing for road construction and other civil structures falls a little bit out of the scope of what we're doing here, but thank you for the idea. We will add it on. And Agret, there are a couple of other questions in the chat. If you wouldn't mind having a look at those, we need to now move on. So if you would unshare your screen, please.
I'm sharing, and I will answer some questions in the chat.
Thank you very much.
With pleasure.
And our next presenter is Andrew Johnston. Andrew, if you'd like to share your screen, please. Oh, I need to make you, yes, all right. Okay, so we're talking today about environmental, social, and governance issues, something which is becoming more and more important in our lives. So, Andrew, we listen with enthusiasm.
Thank you, Tanya. Good morning, everybody. My name is Andrew Johnston. I am with a company called GCS. We water and environmental consultants. And I'm going to share with you some thoughts today on environmental and social governance, which is the ESG, and also a collection of environmental and social baseline data during exploration phases. This is becoming an issue in all the major mining companies at the moment. They are starting to get measured by ESG and ESG standards. So it is really great for geologists to start knowing something about this, because you guys at the forefront of all the exploration, and as a result, you are probably the first people on the ground who can actually make a difference and collect the information required for ESG reporting. So, sorry, let me just go through this. Okay, so basically, it's what geologists need to know about ESG. ESG is environmental and social governance, and ESG S is environmental and social baseline studies and collection of environmental or social baseline studies during exploration. So at the moment, environmental and social governance is on the agenda of investors and mining companies. And you can see a lot of these investors are actually starting to look at mining companies to see what their ESG policies are. And ESG is widely and used as a sustainability index for mining companies and how these mining companies are making profits, either at the expense of the environment or with the environment, and what their legacies are going forward. So investment funds are now also measuring ESG performances of companies, and ESG really looks at the benefits of wider group of employees and communities to projects. So at the moment, we're trying to balance what we call the triple bottom line: is the economic and there's the revenue for the mining companies. We're looking at the environmental impacts and associated issues regarding air, water, and soils, and then obviously the social impact in terms of the mining company and their social commitments to the area that they operate in. So in the social side of it, there is a policy now called the social license to mine, in terms of what the mining company's feedback is or contribution is to the social welfare of the area that they operate. From an economic concern, this is obviously the investors in the mining company want to get some economic return for their investment, and the mining company wants to make some profit. And the environmental issues are the potential impact on water, soils, and air. So the financial institutions have embraced this concept where G is the governance, E is the environmental issues, and ESG is now an acceptable criteria, and there are standards for measuring ESG. In South Africa, there's a move now to look at the SAMESC ESG guidelines, and this is also the SAMESC Codes, where investors have to look at ESG in terms of their reporting for listing on any stock exchange. And the UN EP Commission study of 2015 concluded that failing to consider all long-term investment value drivers, including ESG issues, is a failure of fiduciary duties. And now it's actually in the boardroom, and it's a fiduciary duty for the directors of the company. So, ESG covers a major multitude of things. We can look at climate change, we can environmental impacts, we can look at water impacts, social and human rights, we can look at governance issues, employee relationships, bribery and corruption that we've seen in certain states. And then the authorization from the government authorities as part of the mining license, and also to undertake an EIA or ESHA, which is Environmental and Social Impact Assessment. And the ESHA really considers impacts and recommendations and mitigatory measures that you need to put into place when you're starting a mining operation. So really, the whole ESG is to minimize impacts in a sustainable manner, and it's composed of a bundle of obligations in terms of the mine. And in South Africa, it's usually associated with the mine plan, the environmental management plan, social and labor plan, and also the closure plans. So what I'm going to do now is actually just go into different aspects and different methods of collecting ESG information during a exploration phase. So in terms of the resources allocated to meeting the company's environmental and social responsibilities, you have to achieve a social license to mine. There are massive changes in less developed countries where there is underdeveloped infrastructure. So as a result, there's pressure on the mining company not only to develop infrastructure for the mine that they're proposing to build, but also to build infrastructure that is going to benefit the community at large and potentially the government at large. So this might mean building of roads, bridges, and water infrastructure. It might mean social and labor plans in South Africa, where the mine is obliged to commit to the spatial development plan with the municipality. You need to look at integration with government spatial development plans. You then have to put in some funds in terms of the closure funds for the mine once you finish mining. And then you must make sure that you close the mine in an environmentally and socially sustainable manner. Environmentally, it means that you have to control all the environmental impacts, and social sustainability means how do you maintain the livelihoods of people once mining has ceased. So there's a whole lot of, I'm going to go through this very briefly, but there are a whole lot of issues. There's ESG standards are very well documented throughout the world. You can actually look at equator principles. So if you want to read some background information on ESG, it is available, and there are numerous publications on this. But what I'd like to do, and as I mentioned earlier, you've got the SAMESC and the SAMESC codes, and now the SAMESC codes, which were developed in 2017 for South African companies for registration on the stock exchange. These codes have been accepted and are in line with environmental best practices. So if you really want to see some more or find out some more about ESG and reporting standards of ESG, please go into the SAM's ESG codes and you'll be able to find them there. So really what we're looking at is what information can you as an exploration geologist or a geologist working on an ore deposit collect to assist in terms of the environment, the ESG standards and reporting. So what we've called this is collection of environmental and social baseline studies. So what information are you going to collect during the phases of exploration or even resource drilling, or potentially even when you're mining as a geologist? So it's based on a couple of things. Obviously the legal aspects, we'll go through those. The social aspects is the community and the land use and infrastructure. The environmental is the ecology and the water, and then how you can undertake ongoing monitoring and recording during the exploration phase to add value to the information that you collect. So the headlines are all over at the moment. So, you know, climate change risk widely acknowledged, but really incorporated into strategy. Paladin fields more questions from Kara Kira Sale. And Parenti is to exit higher risk areas in northern Burkina Faso. Codel receives environmental and social license assessment approval for the Mali project. And then you can see the stock exchange, when people do get approval for the environmental permitting for their mining operations, usually there's a corresponding increase in the share price. So really what we want to look at now is that what do we do? What are the objectives of collecting environmental and social baseline studies during your exploration phase? So the benefits of collecting this information, it streamlines the environmental authorization process. It informs the social impact assessment. It identifies required legal agreements and stakeholder assessments. You get an indication of the baseline information, environmental information, that is the ecology, the soil, the water, fauna and flora. And during this exploration phase, you can monitor seasonal variations in, for instance, water runoff or volumes of water runoff, or even vegetation. So early, and allows you to establish an early and lengthy database, and exploration geologists are usually ideally positioned to collect this information. So in terms of the stages and development of a mine and the mining life cycle, your exploration is really at the front of the potential development of a mining life cycle. So we need to collect this information right at the front. It informs the whole mining cycle going forward, the authorizations, the permitting, the social license to mine, and all the ESG concepts that you're going to follow from your exploration phase into the development of the mine. So really, you know, we need to understand now, how do we make this happen? So if you look at a life cycle of a mine, you get a geoscience surveys of potential resource, which is a desktop. Then you look at exploration, which is intrusive exploration and studies to confirm the deposit. Then you look at infrastructure and mine layout design in terms of looking at the potential ore body and how you're going to mine that ore body. Then you look at the development of the mine. Then you get the extraction of the ore, and at the end you get closure and reclamation of the area when you finish with the mining life cycle. So ESBS, environmental, social, and baseline studies, really start getting involved during the exploration phase. So you can do some work on a desktop level to get some of the information, and typically that would be searching some of the databases to see, for instance, if you had red data species in the area that you're doing exploration. And if you have got red data species, you are going to be having to look at some environmental issues to protect those red data species. So ESBS is really in the desktop phase and in the exploration phase. So, so what does ESBS actually do for us? It informs the design, informs the layout of the mine, it informs the location of the mine, it identifies and avoids risks, informs project plans, it gives you proactive intelligence, and then also you can look at the risks that are associated with the proposed development, which is authorization, your risk averse, optimize budget, and minimize schedule. So ESBS, again, as I said earlier, fits in between the prospecting and exploration phase, and this actually feeds information into the total mine life cycle. Authorizations usually occur after the design and developments, and let me go through some of the things that you would need to do. So in terms of collecting environmental and social baseline data, you need to have this data collected in a geographical coordinate-driven system. So there are a number of databases that you can use. eSimon is one of the databases you can look at in terms of cloud-based data, where you can store this data. It doesn't get lost. It's not lost in the Expiration geologist notebooks. And this data then is available to a number of people who will be working on the project to share. So I think cloud-based information storage is probably where you want to go. And you want to collect this data in a time series manner, where you can look at potential things like changes in groundwater levels over a season to see what the variations in groundwater level are and what the recharge mechanisms would be. And as I said earlier, this should be available to all stakeholders. So let's have a look at ESBS from a desktop study and what you can do before you actually get onto site. You can look at the legal review of the legislation and what legislation is going to govern the area that you're going to be exploring. And you can also do desktop assessments of ecology, land use, and social context and water. I mean, you've got some very good images now from Google and Google Earth, where you can actually look at certain amounts of this information. You can look at population, you can look at roads, you can look at servitudes. There's a lot of information you can start collecting about your site before you even get onto site. You can also get some historical data in terms of groundwater, surface water, ecology, and community mapping. And you can identify things like protected areas, important water resources, and communities and land ownership. This is just one of the things that if you looked at a site, you're able to find what farm you registered on. You've got roads, railway lines, pipelines, power supplies, and settlements. And two of the major issues that you're going to face in terms of developing a mine is railway lines for removal of the ore, or road transport to removal of the ore, pipelines to supply water to the proposed mining operations, power supplies in terms of getting power to your proposed mining operations, and then settlements. How many people will you have to move in order to develop your resource? And how do you move these people? Now, what are the relocation action plans, and what is the social impact assessment that you're going to do? So also you can look at the list of legislation reviews. So obviously in South Africa, you look at all the legislative requirements, and there are plenty. You're going to have to look at a number of different acts. You're going to have to look at the Environmental Act, Air Emission Act, Human Settlements Act, Water Acts. You're going to look at ecology. You can look at agriculture. So a number of different legal processes or legal requirements that you'll have to have a look at. One of the biggest things also in this exploration is to get the legal agreements with landowners, and this is you either get individual landowners or community landowners. And this is one of the biggest stumbling blocks that we have in South Africa at the moment, is getting these agreements with individuals, which might be individual farmers or communities, and getting representation from the communities that you're able to sign an agreement that is legally binding. So it's critical that you actually look at these agreements. You make sure that there is landowner consent, and you have an option agreement to say, I am going to be doing exploration on the property, on your property. If I find something, we'll be developing a mine. Therefore, let's reach an agreement now in terms of what I'm going to pay you for your land, and also what the agreement is that we would do if we move people from this land in order to develop a mine, and how do we do that? And they're very strict World Bank guidelines in terms of community relocation programs. So, you know, it's a thing that has to be brought into consideration. And as the more, and the common thing is that the closer your exploration holes become, the more the community's demands are going to be, because they know that you've actually found something in that area. As a result, if you don't have an agreement up front, you're going to be negotiating, you know, with the community who knows that you now have discovered something, and the expectations are going to be a lot higher. So also from a social desktop study, you can do community, cadastral and satellite imagery, you can do land ownership, you can do population dynamics, and you can determine what services that are around your proposed project. In terms of ecology, land use, and assessments, you can look at Google and satellite imagery, you can look at ecological unit identification, delineation of sensitive habitats, you can look at the current land use and what that land use is at the moment, and that obviously feeds into the community and the relocation action plan, because you're going to have to ensure sustainable livelihoods for the communities that you're going to be moving. And then you have to look at the land capability and the agricultural potential of your land. You can look at baseline water quality, pre-mining. We can identify what other impacts have occurred prior to mining. There might be some upstream mining in your catchment. There might be some community concerns. There might be some stormwater issues. There might be some sewage leaks, and you know, there are a number of things in terms of, and here it's best to identify the current state of the water quality in the catchment. You know, as a result, you're then able to determine what potential impacts you're going to have, and also what your receiving water quality is. There's a very interesting concept on the moment, which is what they call as water footprinting. Water footprinting determines the catchment and the yield of the catchment, and how much water is left in that catchment for utilization. So you know, if there's no water left in that catchment for utilization without a detrimental impact to the catchment, you're then going to have to start looking at trading of water resources, or actually inter-catchment transfers to get that water for your proposed mining development. So these are all things that, you know, the geologist can get involved with, and it'll add a lot of interest to your daily routines. You can do baseline sampling. Again, that is probably water quality sampling in streams or in groundwater. You can look at ecological sampling, which is, you know, ground truthing of ecological units and habitats. You can look at seasonal variations. You can look at seasonal wetlands, and there's some major issues in terms of development, and the impact of development is on wetlands. You can sample the fauna and flora, and you can look at the seasonal variations that you have over time. Community mapping is critical. This is the exploration geologist is really the first person who actually interacts with the communities. So the relationship with the communities is critical. You're then able to map the communities, you're able to map how many people are there, what their livelihoods are, what their expectations are going forward, and also to get agreements with the communities in terms of looking at how you're going to go forward with your exploration program. You then have an idea of how the community structure works and who you should talk to in terms of getting agreements signed, whether it is a community leader, whether it's a government leader. You know, it's critical for you to find out how the structure, how these communities are structured and who you should be getting agreements with. Community mapping, there are always dwellings within the study area, so you're going to collect the baseline data from the community as the population, livelihoods, culture, and the household dynamics. And this contextualizes the requirements for resettlement and compensation. Groundwater, very interesting. I think we lose a massive amount of data, and I think Colin Rice has spoken to you about the drilling. One of the critical issues that we as hydrogeologists will come into a prospect, and we have to do a hydrogeological study. And they're probably, I know in some cases, there's probably 100 to 200 exploration boreholes that have been drilled. None of them are open. There's no piezometers in the exploration boreholes. As a result, you have to go and start drilling additional percussion holes to get information that you would require for the hydrogeological study. So it's critical that you try and convert some of the exploration holes, whether it's a diamond hole, RC, percussion, or into a water monitoring borehole that can be used later. And this allows you to sample based on ambient water quality. It also, in your exploration, allows you to identify surrounding groundwater users. You look at groundwater dependent ecosystems. You can look at aquifer potentials. And that aquifer potential is quite critical because that is how much water is going to go into your mine, what are the problems you're going to have with dewatering, and potentially can I use that water to supply my mine with water. You can determine groundwater levels. Is your ore body above or below the groundwater level? You can look at data, pre-mining, water quality and quantity. You can understand potential resources. And obviously, you can look at other things. And really, it is just about understanding the aquifers in the area of exploration. Surface water, again, here, critical. You look at baseline water quality, you look at baseline users, you can do catchment resource evaluations, you can have data on pre-mining quality and quantities. It is limitless the amount of data you can collect during this phase, which actually feeds in. I mean, for instance, you can start plotting flood lines and determine if you have a certain amount of rainfall, what are those flood lines, and you know that the water legislation usually does not allow you to build anything in the flood lines. So it is great that you can start mapping these flood lines and tying that to rainfall events, so you can actually then generate 1 in 20 year, 1 in 50 year, and 1 in 100 year flood lines. Biodiversity, this is land potential. What's the ecological status of the area? Understand the legal requirements and local policies. You can avoid conservation areas. I mean, you've seen a number of these in the press at the moment where people are trying to mine in conservation areas. And the general communities at large have got an incredible amount of power now through the legislative and through the acts that to stop mining companies mining in conservation areas. So although you might have a fantastic ore reserve and you've identified a great ore reserve, if it's in a conservation area, you're going to have problems permitting the mine and getting permission to mine in that area. The other thing you can do is you can map high agricultural potential areas so you can keep the infrastructure away from the high agricultural potential areas. And you can then look at how you're going to place your mining infrastructure on the less sensitive areas should the mine go ahead. Stakeholder engagement, as I said earlier, you've got to identify community leaders, you've got to identify the communication, you're going to have community buy-in and support. You're going to have to manage the expectations of the community. Those expectations might be from a borehole with a hand pump for a water supply for the community, or potential claims against you for damaging stock or leaving gates open or damage to fields. So you have to look at those potential community issues. And all this information is going to be taken and inform the corporate, social, financial, investment focus, and you have MOUs and legal agreements with your communities before you actually go any further with your exploration. So again, stakeholder agreements and exploration activities. You stake a value of the land during the exploration, so you know what you're potentially going to be having to compensate going forward. you get compensation agreements, and you get prospecting licenses in place that you make sure those licenses are legal. For the social license to mine, these agreements with the communities, you're probably going to have to move communities. You're going to look at potential water supplies. You're going to look at community health in terms of clinics that you need to develop. You're going to have to look at provision of infrastructure and services, compensation agreements, stakeholder values, and it all will drive your corporate social investment strategy. So GIS, I know Pedro's going to be talking to you about later, and he's going to tell you a lot more about GIS than I can tell you. So you'll be looking at visual interaction tool for data management. You know, you can inform your layout, you can layer all your data, you can layer all your geology, your hydrogeology, your soils, your vegetation, your flood lines, your communities. So you're able to layer all this information and get this layer mapped in terms of actually using it to inform or decision make how you're going to actually look at the mining process, where you're going to put your tailings dams, where you're going to put your plants going forward. And this is all information that you're able to collect during the exploration phase of the project. So I'm just going to go through the benefits of ESDS and you know, how do we make it happen after that. So, you know, you can't stress this enough. It really is, you know, it's the critical start of any project is start collecting this information. You know, whether it's social information, environmental information, water information, you know, legal agreements, whatever it is, it really informs the project risks going ahead. And I think a geologist is ideally positioned to start collecting this information. You know, you can call on experts to assist him with collecting certain information, but this information, you know, is critical for the long-term project, and it definitely cuts down lead times from when the resource is being quantified to the time when the resource is actually developed, because that's the time it takes. And during that time, you have to get all your legal agreements in place, your environmental impact assessments, and get all the necessary permits and fulfill all the requirements for you to mine. So how do we make this happen? And really, this is you know, aimed at exploration geologists and the geologists to say, you know, what can we do, and how can we bring it to your attention to collect this information, and how do we make this information, how do we put processes in place to collect this information? So, you know, during exploration drilling, you can optimize, you know, you can optimize the exploration drilling for groundwater depths, quality and quantity. The exploration bores can be converted into hydrogeological monitoring holes, and also you can collect geotechnical information. You know, all the core that you collect, an engineering geologist can look at that and start mapping fractures. You can look at RQDs, then you can look at, you know, how stable it is. Plus also, that core is critical in the geochemical assessments of the potential ore body, because during that phase, you can start running geochemical testing to determine what the potential impact is going to be on the water resources of that area. And these geochemical tests take quite a while, because you have to do leach testing, and then you have to do humidity cells. And those leach testing humidity cells, you know, can run anything from 10 to 50 weeks, you know, to actually see what the potential impact of the mining of the ore body, whether it's the waste rock dumps, whether it's the roof or the floor, or whether it's the ore that's left behind, and you know, what impact that's going to have on the surrounding water resources. The Google imagery, you know, you can plot the geology and potential ore bodies. You can detail and document the number of potential households to be affected. You can document crops and the affected land portions. You can look at the land use mapping. You can enter agreements with the landowners earlier. You can, the closer the exploration bores, as I said just now, the greater the community expectations going forward. You can put in your community liaison methods, and this is, you know, you can arrange your community meetings and engagement. You can identify community issues and concerns. You can set up parameters and manage expectations. You can build relationships, and critical that the exploration geologist builds the relationships with these communities going forward. and get agreements signed at the end of the day. So in terms of some of the other things you can look at, you look at linear infrastructure, you can look at agricultural development, commercial industrialized projects, and you can look at rezoning applications, because you're going to have to rezone the area that you want looking at proposed for the mining area from an agricultural to a proposed mining area, and that might involve some rezoning applications that you have to put into place. So you can look at, in terms of the conclusions for collection of this information and how it informs the whole ESG process, you can identify and manage project risks, you can optimize expenditure in the exploration phase, you can inform the design, layout, and alternatives and location for the proposed mine design, you can manage stakeholder relationships and expectations, you can streamline the authorization and permitting processes, and you can provide comparative monitoring data prior to mining, so at least you have baselines to actually measure the potential impact the mine is going to have. And you can optimize the project schedule and budgets, and you can encourage investor confidence, because if you have the necessary permits and everything in place, investor confidence is going to be there. You're able to show that you comply with all the ESG requirements of a potential investor looking at you investing in a proposed mining development. And if you comply with the ESG issues, your investor relationships are going to be a lot easier. Thank you very much for your attention. There are my contact details if you want to get hold of us, and I'm very happy to answer any questions.
Thank you very much, Andrew. ESG is so much a part of everything that we're doing at the moment, and cannot emphasize enough how much geologists need to know about this right from the start. There are a number of questions in the chat box. Let me get to the first one. The difference between EIA studies and ESG studies with the onset of a mine.
The ESG is really an overall global encompassing issue. So EIA would be environmental impact assessment. We're only looking at the environment. Then you get to a thing that they call ESHAs, which is environmental and social impact assessments, which then brings in the environmental and the social aspects into an impact assessment. And then the G at the end of the day is the governance, in terms of how do you comply with the local legislations, and that legislation might be the overall government policies, but also how do you comply with agreements with the communities. So the EIA is part of an ESG program, but ESG is far more encompassing than just EIAs.
Thank you. Okay, Kerry asks, what is the typical investor response when consideration of ESG was good at the early phases, but discarded as time moved on? Have you found that investors will relinquish their shares, or do they look the other way?
I think there is such a lot of pressure on investors at the moment, because those investors might be using public money to invest. For instance, the Church of England is one of the major investors in mining programs, and they've invested in some of the Canadian mines and invested in some mines in Africa. Just to give you an idea, so the Church of England, and I don't know what their values are, but they've decided not to invest in coal. So they've made a policy as an investor, we will not be investing in any more coal projects going forward. So you can imagine what that does to investor confidence. So I think in a more transparent world that we have at the moment, unfortunately, I don't think investors can look the other way. There's just too many checks and balances in place to make sure that you comply.
Thank you. Do we have any other questions? We can take questions live. Just put your hand up, or if you're having difficulty with that, just unmute yourself. I have a question, Andrew. What sort of governance issues are important in the ESG reporting?
I think it comes from a different level, Tanya. You can have governance sitting in a board, for instance, in terms of how does that board behave regarding the governance with that project. Then you look at the governance in terms of complying with the legislation that's applicable to your specific area. So you have to look at that governance, that you make sure that you are not mining illegally and you have the necessary permit requirements in place. The other then is you have to look at the fiduciary duties of a board member in terms of how he transmits the data into the public. So based on those three aspects, I think those are really the governance issues that you're going to have to consider. And those governance issues will change over time. You know, you might have governance issues that you face now going forward. You might look at some other governance issues. So it's a continuously evolving aspect, and it is critical for the mining company to have those governances in place if they want to attract investor confidence.
Thank you. Any other questions? Well, thank you very much, Andrew, for that.
Well, thank you very much, Steve, and thank you for your time.
Thank you all. And on that note, with respect to ESG, I would like to just mention to everybody that later in the year, I think it's the 10th and 11th of August, the GSSA is holding an ESG Inquisition over 2 days. It's a free event. You just need to register. And what we're going to be doing there is looking at what sort of sustainability reports, what competent persons reports and annual reports need to include in their ESG. So we'll be looking at a number of presentations by international organizations on sustainability, what's happening in the international scene, and then a number of panel discussions as to what is happening in South Africa. And the whole purpose of this is to inform the latest SAMESC update, as well as what could be included in SAMREC. So please diarize that. Keep a lookout for it in the GSSA documentation that comes around. So at this stage, we're now going to just have a quick break for the tea. So rush off and get your tea, take your muffins out the oven, and we will see you in 15 minutes time. So let's make that at 10:15. We will restart again. Morning, Prevlin. I see you've just arrived. Would you just like to test your presentation? Just see if you can share without any problems.
Sure, no problem. Thanks, Tanya. Let me see if I can share.
I'm also going to ask you to start a little early at 10:15 instead of past.
That's no problem at all.
Great, thanks. Can you share your screen? There, that's
Okay,
perfect. That
there we
works
go.
fine. Thanks.
Just make
Okay,
sure. Just
you
wanna
can
check one more.
unshare while we
There we go. Cool.
have our
Perfect.
tea.
Thank you.
Thanks.
Great. Thank you.
Maria, you're the other one of our speaker who is here. Would you like to share your screen as well, please? Oh, okay. Thanks, Prepin. We'll begin in 1 minute. I just want to mention to everyone that the presentations are not on the free YouTube channel. I've just posted the Geoskills recording link on the chat. That is where you'll find it. It's not under the free YouTube channel. It'll only be on this link. So with that, let's continue on with our presentations. Next up is Prevlin Chetty from Digby Wells, and he's going to be talking to us about what geos need to know about remote sensing and GIS. So without any further ado, Prevlin, if you'll share your screen and off you go. Thank you.
Well, thank you. Thanks, Tanya. Just a quick sound check. Am I audible?
Yes, we can hear you fine and see your presentation perfectly.
Okay, great news. Thank you so much for this opportunity. It's, if my memory serves me correct, I think it's my 3rd time giving this presentation. Not the same one, I've changed it a bit. But thank you so much for the invitation. I really do appreciate it, and it is something that I am genuinely passionate about. Okay, particularly having come through a bit of an intern system myself, more so in the GIS environment, but I'm always willing to share my experiences and what I've seen thus far. So just a quick a brief history about myself. I am 32 years old this year. I've been in the industry for 11 years this year, so I've been a bit fortunate in that way. I started working while I was in my 3rd year. I did a BSc in geology and geography. I decided to pursue the geographic information side of things. And yeah, I haven't looked back. It's now my 11th year in the industry, and it's been a bit of a roller coaster, something that I've been extremely proud of. So yeah, I'm just hopeful to share a lot of information with you guys today. So just a quick overview of the presentation. Just gonna give you guys a brief introduction to the company I work for. That's Digby Wells Environmental. We're going to look at a GIS overview. Okay, so what really is GIS? I know that a lot of you would have covered this in your theory anyway, but it'll just provide a bit of a foundation for the rest of the presentation. We're going to look at software environments that we commonly operate in and that you will most likely encounter during your time as a geologist. The remote sensing aspect of it. So GIS and remote sensing to me is one, we use the two very they operate with high synergy, so we use it as one technology, but we'll just look into some remote sensing applications. And then we'll look at specific applications in the geological environments that we commonly work with. Okay, so jumping straight into the presentation, just a brief history of Digby Wells. We were formed in 1995. Digby Wells was, well, at least the founding members were originators from Rand Mines. Okay, so they were part of the environmental department. And many of you would know that Rand Mines was responsible for many of the mines on the Western Reef, okay? And they divested from South Africa at the time in 1995, okay? A lot of Rand mines went into Upper Africa, that's now called Rand Resources. You'll see that Rand Resources is also known as Barrick, one of the largest gold producers in the world at the moment. So they're doing extremely well in Upper Africa, large footprints in Zambia, DRC, Mali, all of those kind of countries over there, Sierra Leone included as well. And when they divested, the 3 founding members of Digby Wells actually left and started the company Digby Wells. The name Digby Wells, that's actually the name of the then CEO. Unfortunately, he tragically lost his life, I think about 2 months into the forming of this new company. And in honor of him, the company took on his name, Digby Wells Environmental. So to this day, we still have our founding members that are actually operational. Our managing director is one of the CEOs. So that is Graham Trussler. Okay. So our mission is to be the preferential partner offering environmental and social services to the resource industry. So just an overview of what we do. Pretty much everything across the life cycle of a mine. So from the greenfields right down to the closure aspects. So that's rehabilitation and closure. We've got an environmental management services division. I am part of the Geographic Information Systems division. I actually head that up. There's a noise and air quality division, social services, water geosciences, biophysical services, and environmental legal services. Now, obviously, the geological aspects run in tandem with each and every aspect that we look at over here. So just a bit more into the GIS remote sensing side of things, okay? In terms of our offerings, we've broken that down into 3 broad-based services that we do offer. So cartographic services, that is all of the map making, all of the reporting inputs, all of the graphics that go into all of our Digby Wells illustrations and reports. That originates from the centralized GIS system, okay? We also have a GIS analytics and reporting division. They're responsible for all of the impact assessments, all of the specialist reporting tools that we deal with. So that includes things like your visual impact assessments, historical land use stacks, bathymetric surveys, illumination surveys, and a few other oddball activities that are spatially orientated, okay? We've then got the remote sensing applications. That's the satellite imagery, imagery analytics, historical imagery. We're very strong with our LiDAR data processing. We take it to that next level, and also the UAV drone service. So we don't own a drone. The legislation around that is a bit murky at the moment, but we do use a plethora of service providers depending on which country we would be based in. So at the moment, we've got 4 dedicated GIS and remote sensing staff, and we make use of quite a few subcontracting associates. And between the in-house team, we've got 50 years of combined GIS remote sensing expertise. So that's pretty high for industry norm. Even the team size, you know, to be at 4 or 5 staff, well, actually 5 staff today. We've got a new gent that started today. It's quite a big team when you look at the other consultancies in the country. Okay, so just a quick look at GIS and what GIS really is and what do we refer to. So it's an information management system that deals with spatial data. Okay, there's a lot of other definitions. They get a bit fancy. They use some big words, but in a nutshell, it's a data management system that deals with the capture, storage, and analysis of spatial data. Okay, so when we talk about spatial data, we can break it down into, we can break it down into vector and raster. Okay, so vector refers to your shape files, your CSVs, a few other funny formats as well that come into play, but that's your points, lines, and polygons in that order. Okay, and then you get your raster, which is the image. Okay, so that is the best way to visualize that. That's a satellite image, or even an image you take on your phone. If you zoom in enough, I know the modern phones don't quite allow this, but if you were to zoom in on a Nokia photo, you would eventually get to like a pixel size, that individual block, which is a discrete color. That is the principle of a raster. They work on a series of pixels, which together combine to form a discrete image. And the goal of a GIS is to really use those 2 data inputs to formulate what we call a digital real world representation. So that's always the goal of a GIS, is that we try to recreate the real world in a digital framework, and then we can run some models and simulations. So it does not differ for applications in geology. We use it for the same purpose. In terms of GIS software that we commonly utilize and that we would commonly use, we've got Esri. Okay, so they hold a large monopoly over the market, and that's only because they've really been there from the beginning. Now, remember, when we talk about GIS, GIS is not Esri. They are one of the vendor providers that do exist. So it's only because of that rich history that they have with the software. They've been from the beginning, and they've kind of pioneered the way through for other software providers to come through. PlanetGIS, that's an interesting one. It's a bit of a local solution that we use. We use that for all of our cadastral data, all of our deeds data searches. They kindly run in tandem with the various department custodians. Whenever they release data, PlanetGIS almost acts as a custodian to release that data for us. So they're very reliable in that sense for that. And then QuantumGIS. A lot of you would have worked with QuantumGIS. The same developers that develop Esri, I would say in their free time, they are actually encouraged to write code for QuantumGIS. So works in a very similar fashion. The interface is very similar, but it does get a bit more demanding if you want to run some more advanced operations. Whereas Esri, Esri's ArcGIS, there's a single button that's been created. Hit the button and it runs a script for you. So in Quantum, if you want to maximize your usage, you really need to be a bit adept at your Python coding. Okay, so those are the vector-based offerings, Esri, PlanetGIS, and Quantum that we work with. I'm going to jump straight to the bottom, and then I'm going to go to the middle. Okay, so at the bottom, we've got our raster-based software packages that we operate in. We've got Intergraph, okay, which is ERDAS. ERDAS is now part of that Intergraph group. ERDAS is very popular for the geological side. We use it a lot for the remote sensing analysis, particularly multispectral band indices for exploration side. There's Idrisi. A lot of you would have come across Idrisi at school or university level. A very basic software program, but it's pretty powerful. I wouldn't say we use it that much in the commercial side. We more rely on ERDAS and Envy, but Idrisi is still a popular choice. And then Envy, which is probably the most expensive and the most powerful one of the lot. And the only reason being is that Envy is actually designed to work with hyperspectral data. Now we'll go into that in a bit more detail later on, but Envy is the Bentley of the raster-based imagery processing software suites. Okay, so in between, I've got some additional software packages that we work with, and they really form, or fall rather, in between the vector-based and the raster-based offerings. So that's Gem4D. That's an excellent piece of geological software. We use it for our modeling of 3D bodies, or even 4D bodies for geology. And then there's Global Mapper, which is excellent bang for buck software between the vector and the raster. Very nice for moving between formats, converting, even visualizing data. Global Mapper works very, very well. So this is a typical output that we would produce from a cartographic sense for a geological map. This is using open source data. This is using the Council for Geoscience dataset that we would get from them. This is a vector representation of the data. And this is typically what would go into our reporting side over here. Okay, so this would accompany anything from an environmental impact assessment to water use license. The geological backing of the project area is quite important. And this is in a nutshell what the GIS would basically be able to represent or visualize from a mapping perspective. Okay, so just onto the 3D geological environments. I mentioned we make usage of a software called Gem4D. Okay, so that figure that we're looking at on the very top, that is a stratigraphic representation of the different geological bodies. Okay, and remember that the objective is we're trying to represent that in a spatial framework for advanced modeling to take place. What we're looking at the bottom, that is a numerical groundwater model. And we would feed the data from the Gem4D into a numerical groundwater model. There's various different packages you can use. I know that the groundwater specialists over here commonly use GMS, groundwater modeling software, to do that. And they would represent all of that data in a series of a grid, which has a discrete value. And when they run the groundwater modeling applications, they would run it through the software itself. So that's what you're looking at the very bottom, those oblique views and cross-sectional views. Okay, onto the remote sensing side, and apologies if I do get a bit carried away with this. This is my forte, so I do tend to talk quite a bit when it comes to remote sensing. Okay, but remote sensing refers to the acquisition of information about an object without being physically in contact with it. So what that definition basically expands to our human eyesight is a form of remote sensing. Remember, we're standing, we're looking at something, but we're not in physical contact. And that's really the foundation of remote sensing as a science and what we use it for. So everything revolves around what we call the electromagnetic spectrum. That's the graph or the figure that we're looking at on the left. And all of the energy that comes in from the sun, so we call that radiation energy, can be modeled or mapped on what we call the EM spectrum, the electromagnetic spectrum. Okay, so that's different wavelengths of energy that have come through. Now, interestingly, human eyesight, this is quite a stretch graph. It's actually a lot broader. But human eyesight can only see between 0.4 to 0.7 micrometers. Okay, that's the way our eyes have evolved over time. Certain species of animals can see slightly beyond that, but generally we can see between 0.4 to 0.7. Now, you also see that 0.4 to 0.7, that is your blue, green, and red in that order, moving outwards over there. So it's a very tiny part of the entire spectrum that we can physically see. So the whole goal with remote sensing is that we make use of a much larger part of the spectrum. We can fine-tune sensors to see beyond what the human eye can see. And when we start to do that, we actually start to unlock a lot more information coming from the imagery and the surveys that we utilize. So there's two types of remote sensing that we commonly come across. There's something called passive remote sensing, okay? So what that does is we rely on radiation from the sun. We measure that radiation off an object. Your satellite sensors would typically use passive remote sensing. We've then got active remote sensing. That is a different type of remote sensing. So what active remote sensing does, there's a data signal that originates from the receiver. Okay, so an example of active remote sensing will be a technology like LiDAR, which fires a laser point at an object, or even like sonar, which uses sound waves. So it will send out a signal and it will measure the same signal back. And based on the intensity of the received signal, that's how it will decipher what information we're actually looking at. Okay, so remote sensing includes things like satellites, drones, aerial photography, hyperspectral imagery, radar, and bathymetry. Okay, so that's I wouldn't say that's a real image. It might be a real image of a satellite captured in space. And at the bottom, that is typically what you would see from a satellite at a very coarse resolution. So just a history of satellite imagery and where we've come from in terms of the technology. This was a 1950s program. Quite funny that it's called the Corona satellite program. Okay. It was operational in the 1950s, part of the war, okay, and the satellites were actually flown in a very low orbit above the Earth. So these capsules were launched. It was almost like a rocket. That's the best way to look at it. They were launched in very low orbits. They would take a few images. They weren't designed for a very long lifespan. And what the satellite was actually programmed to do, it would take a series of images. It would tilt at a 120-degree angle, and the film, a physical film, will fall out of the satellite and will get deployed by a parachute. Now, if you tell someone this, they'll think that you're making the whole thing up, but this is really where the satellite technology has come from. This was the foundations of it, and it was someone's job to actually catch that capsule. So they would fly with a plane, and their job was to catch that actual physical capsule, and they would develop the film from that. So all of that imagery is actually available. You can access that we call it the reconnaissance imagery from that Corona program. It's been declassified by the US military, and anyone can now go and access it online through the United States Geological Survey. So this is just some of the imagery that was captured during that program. They imaged numerous parts of the world. It's quite shocking to see how much of imagery they actually did capture. There were various satellites that they launched. They were designated with the code name Keyhole satellites, KH, which is quite interesting because Keyhole is also the same company that started Google Earth in its early days. That was part of the Central Intelligence Agency, the CIA. It was like an offshoot from that. So this is some of the imagery, not great resolution, but pretty good for an historical overview of certain areas in the world. So you can see that they imaged the pyramids for whatever reason. And the right is an image of the Pentagon at the time. Okay, so we've come a long way. Thankfully, we don't operate satellites in the same manner. There's no film that's physically falling out of the satellite. It's more of an up and down digital transfer that would happen from a receiver. Okay, so our modern day operations, MODIS is considered a modern day operation, but it's a bit of an old satellite at the moment. It's got a coarse 250-meter pixel. And we come all the way down to a satellite called Worldview 3 and 4, which now has a 30-meter resolution pixel. So when we talk about pixel, that's the minimum mapping unit. That's the actual size of the maximum object the satellite can sense from space. So theoretically, if an object was smaller than 30 centimeters, you would miss it. You would not form a discrete pixel with an object that's smaller than 30 centimeters. Okay. These are some of the satellite providers that you would come across. Maxar, probably the biggest one of the lot. They've accumulated quite a plethora of satellite constellations that they currently operate. Digital Globe was acquired by Maxar, and they operate Worldview, GeoEye, QuickBird, Iconos, and RadarSat. That's from an old company called MDA, which is now part of Maxar as well. Astrium, probably second biggest. If not, they might be a bit bigger than Maxar. But Astrium is the European company. They are part of the Airbus family, okay? They operate the SPOT satellite sensor, Pleiades, and TerraSAR. TerraSAR is quite a nice one. That is a radar satellite offering. We've also got other solution providers, Planet being one of them, and Planet operate with a 5-meter resolution pixel, and they have something called the Dove constellation. So it's quite an impressive operation. They've got about, the last time I checked, about 250 individual satellites that are in orbit. And they call it the Dove constellation because it's actually a very similar size to a dove. So very small satellites in very low orbit, but they are able to take a 5-meter resolution pixel. So what's impressive about the Planet constellation, they are on a campaign to get a fresh image anywhere on the planet every single day. That's their goal. They're very close to that. I think at the moment they can refresh about a week at a time, but their end goal is to get an image on any point on the planet every single day. So quite an ambitious goal, but I think they are pretty close to that. So over and above that, we've got the European Space Agency. They operate satellites like Sentinel. A lot of you will see Sentinel-2. That's a very popular satellite for usage in the geological side. We use it a lot for the exploration aspects of geology. And then the United States Geological Survey, they act as a distributor for the MODIS and Landsat program. Also some of the NOAA datasets, the National Oceanic and Atmospheric Administration datasets. So this is a typical high resolution image that you would find from a 30-centimeter resolution satellite. This is a solar farm. Okay, and this is quite an old solar farm. I believe that people are discouraged from solar farms like this nowadays, but the intention would be that all of the sunlight will be directed towards the central tower, which will then generate heat, heat some water, generate steam, and then that will drive a turbine to generate electricity. So it's a bit of an older way of doing it. There's newer ways of doing it now that go straight into battery packs, but this is typically the 30-centimeter technology that we talk about in high resolution satellite imagery. Okay, so moving on to GPS, something that is commonly overlooked, has high GIS roots and incredibly important for field work when it comes to a geological perspective. So I remember at the time when I was studying, there were only 21 GPS satellites out there. That has now grown to 31. It's probably grown a bit more than that as well. But to summarize how GPS works, it works on the principle of triangulation and trilateration. Okay, so at any point in time on the surface of the Earth, if you were to take your phone out or even a proper handheld GPS, you are supposed to see 7 visible satellites. That's the way that the orbits have been designed. There's supposed to be 7 visible satellites orbiting above you. Okay, now the more satellites that your receiver picks up, the more accurate your GPS will become. Okay, so I would say the minimum accuracy from a GPS would be about 30 meters. That's if you've seen like 2 satellites. But if you were to unlock those 7 satellites, your accuracy would probably come down to between 5 meters down to probably even possibly centimeter level accuracy, depending on the receiver you are using. So that triangulation procedure that pinpoints your accuracy, that's illustrated by that image on the bottom right. Satellite 1, 2, and 3, they generate these coverage circles on where you could be, and those points of intersection will start to pinpoint your exact location on the planet. Okay, and that graphic, which I hope you can all see, that just shows the orbit style of the different satellites. So at any point in time, you should be seeing 7 satellites. Okay, well, at least I see it's actually popping up to 10 at certain points. Okay, so moving on to LiDAR. GPS ties into LiDAR in a very big way. LiDAR is an acronym for light detection and ranging. Okay, very similar to a technology called sonar, but different in a sense. But the principle with LiDAR is that LiDAR is an active remote form of remote sensing. It uses a laser beam. So it's a class 3 laser beam. It emits that from the actual sensor. That sensor will travel down, hit the ground from the aircraft or whatever platform you're using. And the time that it takes that signal to reach the sensor is calculated very, very precisely. And that would give you a range. So remember, if we've got a range, we can infer height based on the GPS receiver that's on the ground. So that is what is used to generate things called DTMs, digital terrain models or digital surface models. So it's a very, very dense point cloud that you would get from a LiDAR survey. It's kind of a stock standard nowadays in the mining industry. Just a brief history again on where LiDAR has come from. A company called Southern Mapping, they were the first to bring it into the country. They actually pioneered the technology to fire with a camera, the first people to do so in the world at the time. Southern Mapping originated from a company called Eskom. We all know Eskom. They were part of the distribution side on the survey for Eskom. And their job was to measure the sag in the power line. So you would know that the more power you pump through a power line, the hotter the power line gets, and the sag would increase. So the surveyor's job was to measure that amount of sag based on the correlation with the power output on that particular power line. So that was their job, that was their mandate. And as a means of getting it done quicker, they identified LiDAR, which is a very military type of software, type of application at the time in the United States. They managed to get the funding from Eskom to pull the service in, and they pioneered that piece of technology. So it originated in Eskom. They were the first people to use it effectively. It was so effective that they cut down the work that would normally take them 12 months to do. They were completing that work in about 2 months. So they became a bit too efficient, something that we're not synonymous with Eskom nowadays. But they got so efficient that they started contracting their services outwards. And that's where the whole mining industry took hold of LiDAR as a piece of technology. So where do we use this in geological senses, right? So we use it a lot for structural mapping. So LiDAR is able to reveal things like your structural features such as dikes, sills, all of those kind of lateral features. And we are able to pull that out using specialized software packages. So one that's commonly used, PC Geomatica, that's able to detect lineaments or structural features on the ground using that particular DTM. Those structural features are critical when it comes to geological mapping and mineral exploration. On to hyperspectral imaging. So this is where it starts to get a bit fancy, it starts to get a bit advanced. Now, when we talk about multispectral, which is the norm in terms of satellite imagery, that refers to your different band inputs. So that's red, green, blue, that's our human eyesight band. And then we get infrared, which is the 4th band. So commonly, satellites operate within those 4 bands. They do go far beyond that as well. Some of the satellites go to 8 bands. Some of the largest, the coarser resolution satellites go up to about 30 bands, okay? The thing with hyperspectral imaging, we're dealing with about 300 bands. Okay, so those are 300 individual wavelength sensors that have been fine-tuned for a particular wavelength and application. So what we start to generate is not just a 4-band composite, but we call it a data cube. It's a single image that has, I wouldn't say infinite list, but up to about 300 different wavelengths associated with the same image, looking at different parts of the spectrum. So where we use that, we take that image cube and we are able to extract things like signatures for individual features. Okay, so when we look at the broad classification of features on Earth, we have things like vegetation. So that signature that you're looking at on the top, that is exclusive to vegetation. So any piece of vegetation that you would go and extract a signature from would resemble the same shape. The response may drop of that particular curve, but the curve will resemble the same shape all the time. You may get some small individual characteristics that may change, but that shape will be very distinct across all vegetation types encountered. Okay, you can see at the bottom over there, we've got different signatures over there. And just to illustrate, you can see that that original green signature is reflected again for a tree. So you can see the original shape of that signature is still retained. You can see grass as well. You see the same shape that is retained. So all of a sudden, if we are able to extract individual signatures for features, we can actually map them on a very, very detailed scale, something that has been unprecedented before. So just a look at how we use this in a geological sense. The left is a traditional geological map that would have been obtained. So that would have commonly utilized satellite technologies that are a lot coarser in resolution. And the right is a hyperspectral imaged map that will actually start to show you a lot more detail for that particular area. So it's the exact same area, just a different piece of technology that's been used. So this will just show you how far the technology has actually come over time. This is another hyperspectral image of a different area, but this will start to show you individual wavelengths. You start to see some nice fruity colors on the bottom right, and that's what we would use in something called band indexing to derive certain mineral potential maps for exploration. So this is quite a riverine environment. I would assume that they're looking for deposits that would have come from upstream on a river to infer a particular source. This is what a hyperspectral imaging sensor would look like, okay? So a lot of the sensors are airborne sensors nowadays that gets bolted onto the bottom of a plane. They literally cut a hole in the plane and they stick the sensor through there. That's what you're looking at on that image in the middle, on the top. All of that gets processed on a very high-end desktop computer. I would estimate that to be valued at about, I would say they start at about 80,000 Rand, those desktop machines, to be competent to process hyperspectral imagery. They go for a lot more than that, but probably starting at that range. That instrument on the right, that is a spectrometer. So that is what you use to extract the individual signatures from. So the idea would be that you would use the sensor in the field, you would capture a particular signature of an element that you are after, and you would then match that signature to the image that was flown. And that is how you derive those various maps. So this is an application that we worked on a good few years ago here at Digby Wells. And Expiration was one of the first mining companies at the time to get a hyperspectral sensor into the country, for the sake of a project, and they flew the whole operation, one of the operations in Mpumalanga. Now, one of the things that we were able to pick up was jarosite mineral detection. Now, you'll know that jarosite is commonly associated with acid mine drainage. It's one of those byproducts that come from it. And you can see that this leachate dam at the bottom over here, it's actually downstream of a workings area on the top. This is an abandoned coal working area to the right. That leachate dam was actually been designed to catch some of the seepage of water and mineral contaminants coming before it hits this water side. So you can actually start to detect all of those jarosite byproducts in that particular catchment area. A little bit more terrifying, same project. You can actually see that the dam isn't functioning the way they're supposed to. We can actually start to pick up additional concentrates of material leaching out of that dam straight into that river. So this is discharging straight into the river from the dam. Okay, so moving on to subsidence monitoring. This is a different type of technology, but we commonly use it in the mining context. Okay, so a broad sense or definition of subsidence, it's underground mining cavities, which can result in a lowering of the Earth's surface. Okay, so this is very common in the South African context because of our history with coal mining and gold mining. So subsidence is a reoccurring problem. There will always be a market for subsidence monitoring in the country because of our historical context with coal mining in the country. Now we can actually monitor subsidence from satellite technologies. This is an example for Japan. Okay, so what they use in terms of units of monitoring subsidence, they call it millimeters per year. They refer to it as velocity, but it's really millimeters per year of subsidence happening. So you can see that this is an island context over here. This is on the edge of the island, and you can actually start to see where the largest amounts of subsidence are occurring. So this is between 1993 and 2017. This is a video just to show you the results from subsidence monitoring and how that actually relates to groundwater extraction. So you would know that groundwater wells are commonly drilled. They extract water, and over here you can actually start to see the correlation between extraction and subsidence over time. So we'll just let this graphic play. It's a little exaggerated, so don't expect to find a massive hole in the middle of this feature, but that will show you the actual modeled subsidence rate linked to groundwater extraction. Okay. Okay, and then just to end off the presentation, Tanya, I just want to confirm, can you still see my screen? I'm sharing a Google Chrome screen.
Yes, we can.
Okay, great, cool. I'm just going to take you into some applications that we commonly utilize on a web GIS environment. It's a very different GIS approach. It's something that's been used more and more in the industry at the moment, but this will just show you how we actually tie in all of the technology for, I would call it a solutions-driven approach. If I can remember my password, just hang on one second. Yeah, just hang on one second. Sorry about this. Okay, almost there. Okay, so this is that same subsidence monitoring program. This is one that we actually implemented for a client. Okay, and what's quite nice about this whole thing, this is a coal mining operation. This is undermined areas of concern that were identified from a survey. And you can actually see what's happening with the subsidence over time. If you click on an individual point, you'll see that you are able to pull up measured degrees of subsidence in terms of meters over time. So this will be linked to the underground workings, what's been happening. This is also groundwater dependent. So this is an integrated project monitoring groundwater as well. And you can actually start to see over the different years what the different subsidence rates for each point or location is across the program. Okay, so just jumping onto another web map. This will be the last one that I'll be sharing. Okay, so something that's commonly overlooked is the role of GIS in mine closure. So we talk about, the full life cycle of a mine, and this is a pretty important one. Part of the closure cost estimate is getting a detailed bill of quantities on what exists on the mine. So remember, when you close a mine down, the mine actually has to rehabilitate this whole sector of land. So that means stripping all of the infrastructure, rehabilitating all of these dumps to the state that it was either before or an improved state. That's often a negotiation between the mining house and the municipality or the Department of Mineral Affairs. Okay, so what happens is in this web-based closure model, we are able to actually build in the closure cost characteristics into the actual model itself. So if we click on a particular building, you'll see that you'll have a whole lot of detail that'll pop up. That's the name of the building. That's the cost of closure for that particular building. And it'll also give you some additional context. So that's the cost of closing that particular structure in relation to the entire operation. So this crusher, if we were to actually close this processing plant over here, it tells you that that's going to be R1 million just to close down that crusher operation. So what's quite nice about the web-based GIS environment, you can actually build in individual filters. It operates on a very similar platform to a desktop, just that you are now not software dependent anymore. You can actually operate this whole thing just from using a Google Chrome account. So you can actually filter between different data styles, and you can also draw, if you wanted to calculate the cost of closure for a particular area. I'm just going to draw a quick one. If you only wanted to close down that area over there, you can draw it, you can click get results, and what the platform will do, it will generate a report for you on the bottom right over here. Hopefully it's not too slow. Okay, so it's going to tell you, okay, cool, there's 29 matching features. And when we say generate report, it will actually calculate the cost of closure only for these particular buildings over here, which I see it's not doing right now, but that's the idea. Okay, so that will conclude what I've got to share. If we have some time, I believe we can go to some questions. Tanya, will that be fine?
Yes, Prevlin, indeed, that will be fine. We have a couple of questions already on the chat. The first one from Michael is, does Gem4D have a Python kernel for data visualization?
Okay, so Gem4D is it's an open source campaign at the moment. It's developed by a company called Baserock. Now, from the user interface side of it, no, I would say that that's probably restricted, but I don't see why not. I believe that you most likely would be able to get that Python encoding section of it. I think that you would just have to get in touch with the supplier for that. So it's a company called Baserock. I believe the gentleman's name is France. He's actually the guy that's coded Gem4D. So it's open source at the moment. I do know that they do have an intention to go commercial, but at the moment it is still open source. So I think that is something that you can definitely contact Baserock about and then just find out more detail.
Then Nadira asks about the accuracy of SRTM topographic point data.
Okay, so not great. SRTM's latest iteration is 30-meter resolution. Okay, so when we talk about resolution, that's the pixel size of the elevation point. The accuracy would probably be in the region between 10 meters or so, 5 to 10 meters. 5 meters at its very best. I would say that you're looking at about 10 meters. So I would definitely also recommend ALOS. ALOS is more temporally relevant. It's a lovely piece of technology. It's a Japanese-based satellite that is now decommissioned. But what's interesting about ALOS is that it consisted of 3 individual sensors, something called pulsar, prism, and AVNIR. Okay. Now the prism sensor was a 5-meter resolution sensor, and when ALOS released their offering to the world for free, they resampled all of the data to 30-meter resolution. So what that means is that some of that 30-meter resolution data would inherently have the accuracy of the 5-meter prism solution. So I would definitely encourage people to use that ALOS offering. So it's a Japanese offering. The way to find it is Google AW3D30, and you would come to a download page where you can access ALOS.
Carlo asks, what instruments were used to capture the subsidence data that you showed? Was it LiDAR or what?
Yes. So that was a very high-spec LiDAR series of surveys. So what we utilized at that point, that was client-supplied data. Now remember, when it comes to LiDAR, you've got a certain vertical accuracy association with LiDAR. I would say that you've got an absolute accuracy, we call it golf ball accuracy. It's between 2 and 5 centimeters between one survey to the next. So that is something to take into account when it comes to LiDAR for subsidence monitoring. So any subsidence that is smaller than that, you would likely miss on LiDAR. That will not be the case with radar from a satellite. Radar with a satellite is extremely accurate. The pixel size may be bigger, but you can actually monitor millimeter size accuracy over a time period that's long enough. So yes, for that particular project, we use LiDAR.
Okay, then there's somebody wanting to know about how to learn more about false color images, band combinations, and band ratios. Do you at Digby Wells do events, webinars and things like that dealing with these issues? Or is it something that you would like to chat to the GSSA about doing?
Look, I can definitely see the value in it. We do host a series of webinars throughout the year. I would say with the onset of COVID, that is something that we've developed a lot more competency for, is having those online webinars. I can definitely see the value in having a remote sensing focused webinar. And yeah, Tanya, it will be a pleasure to engage with GSSA to see how we can facilitate something like that. Okay,
we'll take that offline and chat about that further. Okay, and then there's a question regarding postgrad students looking for projects. Does Digby Wells assist in that case?
Yes, we definitely can. We definitely can. So if you do have a query, you are all welcome to contact me directly. We can then at least steer you in the correct direction with regards to what data we have in-house, which clients you can likely approach. Because remember that when it comes to data, the actual ownership of data doesn't belong to Digby Wells, it actually belongs to the client. So if you are able to get an approval from a client to use their data, we can definitely steer you in that regard.
Then one last very quick question. In general terms, what is the costs of a LiDAR study?
Okay, so I would say the minimum cost that you're looking at for a LiDAR area, I don't think they would bother for doing a survey that's less than 100,000 Rand. It will probably start around there. It depends on the size of the area. These surveys get expensive very, very quickly. It's because of the size of area that they actually have to cover. With that said, a lot of the cost is actually mobilization, getting the aircraft to the actual site. The cost of flying a survey is not that expensive. The cost of the data processing is not too intensive, but the mobilization fee is often what throws a LiDAR survey way off. You know, it gets expensive very, very quickly. But with that said, the data that you get from that survey is incredible. It is the Bentley of the different data suites, and it's often required. There's no way of trying to get around doing a LiDAR survey.
Rivlin, thank you very, very much. As usual, a most interesting and informative presentation. So if you can unshare your screen, please.
Well, thank you. Thanks, Tanya. It was really a pleasure, and good luck for the rest of the sessions.
Thank you. Our next presentation is from Glenn Waila from Wits University. Glenn, if you would like to share your screen.
Is it visible on your side?
Yes, you did. You put it into presentation mode. Mm-hmm. There we go. We can hear you, we can see you, and we look forward to learning about big data and machine learning.
Thank
Thank
you.
you.
I'll just share my camera for a few seconds, because I'm not sure who have met me and who haven't met me. Most of the people have seen me on a photo, not in person. So for the purpose of today, I would like you to take you on a journey where we are speaking of big data analytics and machine learning applied to geosciences or for geologists. And to do this, I just want to start somewhere. So as a parent, you get an opportunity to relive your childhood again. So I tend to watch a lot of Japanese anime. And with this, in one of my Netflix accounts, what I tend to find is after watching one of these animes, Netflix tends to recommend a number of other forms of animes. And some of them are things that I'm not even interested in watching. And with this is the reason when we're speaking of big data analytics and machine learning in geosciences, we're actually speaking of something completely different, because in the commercial and the tech industry, a decision that you have to make with machine learning, you can simply just skip and go and select whatever movie that you want to watch at no cost. Whereas in geosciences, we're dealing with data that involves high-stake decisions. And by this, I mean that you cannot just go to any particular place and sink a shaft. And if you discover that there is no commodity and you move on to the next one, the same thing, you can't go around and drill more boreholes for no reason, because it's going to be more expensive. So unlike in the commercial and the tech industry, machine learning in geosciences become more of a key decision-making tool, not just a tool of saying we want to navigate or we want some fancy type of visualization. And when it comes to visualization itself, there are specific data sets, especially multivariate data sets, that do not allow us to view them in 2 dimensions. And for many years or for many times, people have looked at data and only visualize it at most into 3 dimensions, not even in 4D patterns. And machine learning offers that opportunity for us to be able to visualize data accurately and see all the characteristics of the data in all different dimensions. The third point why many people or many geologists should be using machine learning is mainly that we deal with sparse samples. We usually sample a very tiny place, and we use these particular few points to estimate a very large volume of rock, or to even make interpretations that may result in large financial ramifications. The other one is that we deal with a lot of samples that are full of heterogeneities. And with this, we need something that can help us to deal with these high degrees of uncertainty. And for this, myself and a friend of mine, his name is Steven Zhang, about 6 or 7 years ago, we started playing around with machine learning. And we're looking at many things. The first one was a grade prediction using machine learning for different commodities. The other one was mainly to do geodomaining and facets classification. And the last one was to ensure that we reduce the risk by quantifying uncertainty in geological models and to create some sort of simulations. And with this, as a small type of venture was born by the name of SmartMin. And our main purpose, we are mainly focusing on equipping mineral resources professionals, be it academics and professionals, to rapidly build models, geological models of any form, be it for resources or for academic studies, and also to ensure that they deploy them rapidly without having to worry about extensive coding. But you may ask yourself, why should we be doing machine learning if I have just mentioned that we're collecting sparse samples? So according to IBM, they have actually put in 5 main characteristics of what we should consider big data. So I must say also that geosciences have been dealing with big data far long before the technology and the commercial industry started dealing with big data. As much as Netflix is now far ahead of geosciences, or Amazon is far ahead of geosciences, but I think for some reason we have contributed a lot into what has become known as big data. So how do we know that we have big data? We typically have 5 characteristics. The first one is that the volume of data that we collect, so many samples that we tend to collect, and most of the time they are difficult to visualize And to give you an example, in an iron ore mine where we analyze over 5 different elements, you'll find that we only focus on 2 that are good indicators, and 1 being the iron itself, and the rest of them, such as manganese, sometimes tend to be ignored, or we don't really know what to do with them if that is not our main focus. The second one is more of the velocity. So every day in any operating mine, samplers go underground, or grade controllers go on surface and do a lot of sampling. So it's more of a continuous type of a process. The third one is that there is a lot of variety of this data. So data come from different sources. We have surveyors feeding us data. We have mining engineers feeding us blasting data, geologists collecting mapping data and chemical data, geostatisticians also producing models that we utilize. So data come from a variety of sources. The other one, which is number 4, is that the data acquisition changes during the project stages. So when we're still busy exploring, there are certain limitations. So there are certain things that we look for. So we may even focus on indicator minerals instead of focusing on direct commodities that we're looking for. And then lastly is the veracity of the data, that the data has various level of accuracy. For an example, as geologists, we tend to deal a lot with observations, and with the observations, they may differ depending on who's collecting data. Whereas when we speak to surveyors, they deal with accurate measurements, and when we speak with the people who are working in the geochem lab, they deal with a lot of quantitative and measurable type of data sets. So there's different levels of data quality that we need to look into. And with this, I just want to remind anyone who is actually in the audience that you have been doing machine learning since your 7th or your 8th grade, when we're being taught about the gradient of the slope, or the slope of the gradient. And we're taught about the formula y is equals to mx plus b or plus c. That is exactly the foundation of machine learning, because what you are looking at here on the figure that is far on the left-hand side, it's actually showing us how can we use certain products that we plot in the x-axis to actually predict a particular variable. So on the left-hand, right-hand side, just to put it into context, look at the x-axis. Let's take we have a specific deposit and we have measured its alteration index. And from the alteration index, what we can simply do is to say that, is there any changes in percentage of a particular commodity, in this case, in the grade of copper, with the changes in alteration? And from this, we can just draw a simple straight line equation. And from the straight line equation, it means if we know alteration percentages, we can also know the content of copper. But in addition to this, we can actually also feed some sort of a model. There's a bit of a background in the back. If somebody can mute their mics.
I have just muted them.
Okay, thank you. So what you can also do with this straight line equation is to fit some sort of a model that fits the best data points. And from just looking into these 2 lines, you can see we have this greenish squiggly line, which tends to fit the reddish data points, which we can call it more of the model training data set. And then we also have the solid, the dotted black line, which is not really fitting all the red points on the testing data set. So machine learning using a straight line equation simply tells us that sometimes we have to compromise between the quality in terms of the variance, or we have to compromise the quality in terms of bias. So you can see that the dotted black line is actually compromising more of bias, because it's actually moving away from the data points, is sitting somewhere in between. Whereas when we look at the variance, the green squiggly line minimizes the variance because it's predicting exactly on the testing data set. And how we test this in machine learning is to create more of a testing data set where we take unknown data points and we try to predict this. And from this is where we can decide what sort of a model are we going to be fitting into our linear equation that you see in here. And what we typically do, which everyone does in many things, is to measure the sum of squared residual. In this case, I just call them SSR. And you can see the green squiggly line has yielded more of a higher order lines, whereas the black line has yielded slightly a lower squared sum of residuals. And with this, we can decide that as a model. This does not mean all machine learning models are linear. Most of them are non-linear because we typically deal with a lot of non-linear type of fractions, and I will deal with that in detail. But before I do that, I have also noticed a trend that is developing to say that with us in the mining sector or in the mining and metal sector, most of the data that we have been working with is quite complicated, as I have mentioned before, and we tend to ignore much of the useful information because we don't know how to analyze them. And typically there is so many divisions. So there are people who are focusing on survey, as I have mentioned, there are people who are focusing on mining, there are people who are focusing on geostatistics, and there's also traditional approach, which focuses on qualitative mapping. Preven, who was actually my former classmate who have presented just before me, focused on GIS and remote sensing. So with this, there tend to be a disconnect sometimes on how do we utilize this data. So I think now is the best time to actually develop a new type of a geologist without replacing the older one, where we combine different disciplines and we train this new geologist to be able to at least do something from the domain expertise, meaning fundamental geology, capable of doing statistical modeling such as geostatistics, and be capable of doing some coding which can enable them to become machine learning geologists. And what do I mean by this? For this, I'm going to use some sort of a workflow, and I will dive deep into this. And this will be mainly focusing on what Andre has called machine learning engineering. So typically, before we start any machine learning project, we have to have a number of people. Firstly, we have to have some sort of management involved. It's not going to be done by somebody who was far junior alone. We have to still have a mining geologist who knows what's happening in a particular mine or in a particular exploration project. We also need a resource geologist who knows what's happening with the data sets. The other thing is we also need the senior mine geologists or chief geologists or senior exploration geologists, but we also need people from ICT to assist us with our connections and so forth. And then we also need this new form of a geologist, which for now, I will call a machine learning geologist. And the main issue is to first identify a problem. I have been identified by a number of people, including companies, where they say we have a large data set, we just want you to come with your machine learning algorithms and do something for us. But unfortunately, it doesn't work like that because machine learning doesn't solve problems where we don't know that there are problems. So the key thing in machine learning is to first define the problem, what sort of things you want to sort out. Do you want to predict grade in situ without doing chemical assays? Do you want to create geodomains for resource estimation, or you want to create a resource estimation based model? So that's the first key thing that we do. And secondly, from there on, two people are going to start working together very closely. The first one is going to be the mine geologist and the resource geologist to sort out the data, because they understand what's happening more in the operation or in the exploration discipline more than anyone else. And followed by this is a whole suite that is going to be done by the machine learning geologist, which includes feature engineering, model training, model validation. And then once all these processes have been completed, they are going to meet again with the resource geologist, and the model is going to be handed over to a senior or a chief geologist. So I'm going to break this down into different components, and I will close off with a number of case studies that we have done in different deposits and academic studies. So the first one is data collection and preparation. I tend to spend more days and more hours doing data preparation and data collection because data comes in all forms of types and different scales and all that. And as geologists, as I have mentioned, I will use a typical case of the Vets Basin where I've spent most of my time. So what you will notice here on the top section of the table, we have coordinates X, Y, and Z, and then we'll also have the sample ID. And on top of that, we measure something which we call the channel width, which is actually the thickness of the reef or the ore body. And we'll also measure the percentage conglomerate. Yeah, I just named it conglomerate fraction, and then the pebble size, packing density, and all sorts of other attributes. And on top of that, we do chemical assays, which you see on the far right. But if you want to do machine learning, I cannot go and do any prediction on something which is called well-pegged or sub-rounded or high. So what we do here, we do feature encoding. And by this, there are a number of ways to encode features without losing the typical characteristics of the data. So the one that people typically use is called one-hot encoding, and otherwise is known as a dummy variable. This is a method of converting categorical data into several binary columns. So it means if there is an occurrence of a particular number, I can assign the number 1 And if it does not occur, I can assign the number to. But if I have multiple variables, it means I can use alternative methods that will change. For an example, something that is moderately packed is going to be assigned a number 1. Something that is well packed is going to be assigned a number 2. So this is what you typically do when you have qualitative geological data. The second thing that we do in machine learning is what we call feature engineering. This is more common by those who are professing in geochemical studies, because with feature engineering, we typically do it in the following manner. In a simplified geological sense, we usually work with elemental ratios. For example, if we are dealing with sediments of some kind, we can take the ratio between zircon and nickel. The zircon will be representing material or sediments that are coming from more of a felsic-based provenance, and nickel is going to be representing sediments that are coming from a provenance that is more of a mafic enriched or consisting of mafic igneous rocks. And with these ratios, we try to do some sort of dimensionality type of modeling in geochemistry, but that becomes insufficient when you're dealing with large chunks of data, especially more in an operational level. So what we typically do is we'll take a bunch of elements that we have analyzed from a particular deposit. What you're looking at here on the left-hand side is an iron ore deposit coming from the Acing iron ore mine. And with this, what I simply did was to take all those elements and say, I'm going to be running machine learning here, and I need to know which features are more important in predicting the type of rock type. So the rock types in the typical iron ore type of a deposit, you can find things such as banded iron formation that contains a lot of hematite or magnetite. And then you can also find shales, breccias, and conglomerates and so forth. So here I was doing a classification problem where I wanted to classify different rocks, and I have lined this up. Typically, if I have used my own visual inspection, I was going to say iron is the main definer of a typical element. But you can see in this case that calcium was the one that was more predictive in terms of the classification. The other one that we tend to do is dimensionality reduction. People have been using principal component analysis for years for different reasons. But with the principal component analysis, we can also use this to reduce the dimensions of the number of components that we're going to be feeding into our machine learning algorithms. And what you see on the right-hand side is a typical PCA showing isolations of the different rock types that are known to contain iron in this particular deposit, where also on the left-hand side is the importance of each and every feature in classifying these different rocks. The other thing that you may come across, which present challenges in many ways, is that you need to understand what sort of algorithm you're going to use. So over time, people have actually looked at the number of samples that you have. They have also looked at the type of programs that you're going to be addressing. And with this, they have come up with categories to say that if you are going to be doing a classification problem, you can do this with less than 100,000 samples. And you can do this as little as 100 samples. And if you're going to be doing something that has to do with clustering, it means you can also do this with less than 10,000 samples. And if you're going to be predicting something, which is more of the regression side, here it's where that you need almost 100,000 samples, but you can still work with something less than that, depending on what you want to do. And then lastly, they have also looked at dimension reduction. The first one that I have told you is randomized PCA. You can also do things such as kernel optimization and isomaps and a number of different type of dimension reduction. So before you choose an algorithm, you don't just go there just simply because you have data. You need to look at the type of data that you have. You need to check whether you are having more of labeled or unlabeled data, which will enable you to decide whether you want to use the so-called supervised or unsupervised machine learning. And on top of that, you also need to look at the structure of your data set. If we look at something here, there is something which is more common. Again, this falls within the algorithm classification. You will hear a lot of people speaking of all L1 and L2 regularization. And what they typically mean by this is that if we are dealing with a problem that requires us to estimate more of the median in a data set, then we might as well work with what has become known as the L1 norm. But if we want to estimate the mean on the data, which helps us to avoid overfitting, we may deal with what we call L2 norms. And with this on the left-hand side, what you're looking at on the top side is just a simple data set. You can see that it behaves simply in a polynomial manner. And with this, I have fitted a number of polynomial. The first one is just 1 degree polynomial, which is a simple straight line equation of y is equals to mx plus b or plus c. Then the other one is more dealing with the second degree of polynomial, and that is the blue line. And then we also have the 100 degrees of polynomials. So sometimes people tend to overfit the data, which is more of putting these 100 degrees of polynomial. And again, it results in a concept of saying that you are creating a very bad model, which is going to be appearing quite nice when you're doing your testing work, but when you try to predict new data set, we are not going to be able to do that. Whereas the one that fits the data well, as much as it's not touching each and every point, in this case was the second degree polynomial. And with this, it cuts nicely across the different sets of data points. Those who are familiar with the concept of virography, you will notice that when we fit a virogram too, we do exactly the same thing. We don't try to fit each and every point, but we go through the points as long as that particular model is representative of the data sets, not only for particular individual spatial locations, but for the entire domain that is going to be estimated. And by this, then we need to also look at this, then how do we decide between the accuracy of the model and how to interpret a model? Many people, every time I speak of machine learning, they ask me, can you show me a neural network model type of a thing? So it doesn't work like that. We also need to look at two things. Are we aiming to do supervised or unsupervised learning, or we want to do both of them, or we are going to be focusing on how to interpret a model or how to measure the accuracy of the model? And from these, there is a different criteria that is utilized. One, if you have a model that you can easily interpret, and the simple one is the straight line equation that I have showed you, which can be done using ordinary least squares, we can use now more of a high interpretability model, but it's going to be less accurate. But if we want to do something that is actually somewhere in between, we can do assembly-based methods where we combine a number of methods and we pick the one that performs much better. But sometimes we also need to work with the so-called black boxes that we don't really understand sometimes how they generate the results. It means we can have an ultra complex model, meaning that we can interpret it, but the accuracy is very high. So we don't really know what this model is doing. And for an example, this could be the neural networks. And as I have mentioned, don't go for any complex algorithm when you're still starting to do any machine learning type of a problem or trying to use machine learning. There is no free lunch, and this is a well-known theorem in mathematics that the fact that something is quite complex and so forth, it doesn't mean that it's always correct. Because, for an example, we can only understand neurons when they are operating on their own, but when they are on their own, they don't do much. It's only when you have millions of them that they perform a specific function that can actually help us to do something. So I would recommend that for anyone who's going to be starting a machine learning project, don't just jump into artificial neural networks. They sound very attractive, but you may not even understand what they are doing. But once you do more and more of this, then they become more simpler to explain. Let's look at the model training. What do we do exactly when we're training the model? So when we say we're training a model, there's a number of things, thanks actually to the advances of many people who are contributing on the open source type of platforms such as GitHub, where many people are developing parameters where we can fine tune the model. So I'll give an example with a support vector machine type of an algorithm, where before you can even do the prediction, in typical kriging, we call this post-processing, where we take the points and we try to predict them within themselves, and we use more of multiple, we use more of an integrated approach to decide what sort of block sizes we're going to be using, what sort of slope of regression do we need, and what sort of kriging efficiency are we expecting to get by using the points, so that when we krig the blocks, at least we can accept the results that comes out. In machine learning, we do exactly the same thing. There's a lot of pre-processing that tells us what sort of parameters we need to put into our data set that will result in the highest accuracy. And what we are looking at here on the left-hand side is more of a different classification problem. We are looking at the optimum classification boundary that can actually help us to assist us in choosing the right parameters. And on the right-hand side, you're looking at the validation accuracy before we even do this prediction, where we are calculating what we call the C parameter and the gamma value. And with these two parameters, they help us to find out at what sort of optimum parameters can we condition our machine learning algorithm. So what you're looking at here, you can see that in this particular one, where we have a C of almost 1 and a gamma of 0.1, this is where we have the most darkest block. And that simply means that this is the optimum conditions that we should set in the machine. And once we know how to do conditioning of our model, we need to evaluate how they work. And to do this, there are a number of parameters that you can apply. We can look at the union of numbers, as you're seeing here, by measuring what we call the Jacob index, or we can do a confusion matrix. I'm not going to go into the detailed mathematics because of time limitations, but I'm sure one day we'll have a workshop where I'll spend more time explaining what each and every one does. But I'll just use a simple example of a confusion matrix where we plot anything that is more of true positive and true negative cases in this quadrant here, so the first quadrant and the fourth quadrant, whereas the opposite of that, or diagonals of that, is more of the false positive and false negative. And this can tell us, based on known values or known data set, whether we're doing the right thing or not. The other model that we tend to use in machine learning to measure our accuracy, besides the sum of squared residuals, as I have mentioned, that is more considered standard, or mean squared errors, we can look at the F1 score. And the F1 score is actually quite useful because it's calculated in two ways. First, we need to calculate what is known as the precision score. And this is a measure of accuracy provided that a class label has been predicted as either a true positive or true negative. The second one is what we call the recall score, which measures the sensitivity of the model. And the last one is based on the log loss, where we can use the log loss in cases where the outcome of the classifier is a class probability and not a class label, like a case of logistic regression models. Once we have done that, we have to evaluate the model. There's all sorts of stages that needs to happen. So it means this is where we'll also choose the candidate model, refine it further, and try to find a way to deploy it. And how we do this is we look at a number of ways where we can deploy the model and put it into practice. And for this, there's a whole lot of architecture that is involved. The first one is that there has to be a particular place where this model is stored. There has to be some sort of a platform for verification of this particular model. And on top of that, there is both testing and training and testing data set and unknown data points that have actually been utilized. And once we have that, it means now we need to serve the model and ensure that we maintain it. And this is where it gets back now to the people who are going to be deploying it. And for this, we develop a lot of streaming to make sure that it's usable. So all those codes that have been developed in the background tend not to make it now to the final stages. So I just want to give you a number of case studies as my closing remarks. And forgive me if I go over time by at least a couple of minutes. I'll try to make sure I complete on time. The first one that you are looking at here, typically when people do simulations, get a bunch of points from a particular mine and they do sequential Gaussian simulation based type of approaches. What we have developed with Steve is that we have developed a way to simulate an ore deposit. So instead of simulating just particular points and use them to simulate a deposit, we have actually taken a mined out portion of a mine, or a mine in this case, on a mine scale. And what we have done was to create a model that can simulate the deposit entirely. And from this particular deposit, it means we can take samples to see how good machine learning algorithms perform. The other thing that we have done, thanks to some of the work that was done by Michael Patch, on more of calculating the p-values or the percentile values of different portions of the data points of the model. So what I have simply done here was take this model, take about 1,000 samples and see their distribution in this case. And with this, it can help us not only to study things in an academic sense, but to actually simulate the entire mine based on known particular values on the mined out area. And from this, we can take simulated samples. And from these simulated samples, we can feed them either to kriging, or we can actually continue with machine learning. And as we continue sampling in that particular mine, we can just do that for verification purposes to see if our simulated deposit still behaves the same. So this is what I have showed you. What we have simply done was to take that exactly that model, we sampled that model, and from this sampling, we did all sorts of things. And the first one was to look at the typical things that geostatisticians look for, which is the variogram, and to look at whether a variogram can be utilized as a single entity to determine block size, of course, in addition of a number of parameters. And we played around with the so-called Crick's relationship, which is more of the dispersion variance calculated here in the case of the variance of the averages, and also the weighted average of the variances in a particular domain of some kind. And with this, we managed to also develop a model that do automated variogram fitting. As you can see here on the right-hand side, this was not fitted by me on as a person, but it was automated, and the variogram maps on the right-hand side, on the left-hand side, do assist us to know which directions are more continuous in a particular deposit. The other one that we have looked at is more of what sort of noise and errors can contribute to incorrect machine learning prediction. And by this is, if I take 10% of badly sampled data that no QA/QC was done and try to do a machine learning algorithm into that, can I predict something that is much better? What we have noticed is that the machine will still predict some sort of a reasonable result, but there will be some sort of skewness, which is caused by the noise or the data set that you have introduced with bad quality. As you can see here from this normalized probability distribution functions on the left-hand side, and you can see the misalignment with the cumulative distribution function on the right-hand side. So this assists us to also know to what sort of errors or how off can we be if we use bad data in our resource estimation data. The other one, which is quite common, was to take exactly the simulated deposit model, including some actual mine data, and we did a lot of conditional simulation, but we did not just end there. We calculated percentiles into this, which is typically done on multiple indicator-based kriging. And with this percentile, we're able to reproduce, again, exactly what we have simulated in a deposit, meaning we can rely on simulation, which help us to reduce uncertainty in a particular deposit. The other one that we have done, and I will complete soon, was to take a bunch of geophysical data, all seismic data that were measured in a very large area. I'm talking about deposits that are over 35 kilometers in length and over 20 kilometers in width. And we took this also with some samples that were collected underground, and we formulated some sort of a workflow. So typically what I do when I have a problem like this is to create a workflow, meaning that before you rush into coding items, you need to do what we call pseudo coding, where you simply sit down and you draw sketches and you create logic on how the algorithm is going to work like, so that when it fails while you're busy coding it, you know where to go and change. And then from this data set, what I have simply done, this was not done by any of the commercial software. This was actually done using Python. So I can now automatically create wireframe of the entire deposits, be it for the faults or dikes or reef horizons. What you're looking at here in purple, you are actually looking at one particular reef, and other one you are actually looking at the VCR, and on top of that, we're looking at the black reef. And what we see as a wireframe type of wire mesh type of a thing is going to be a dike, and below that next to it is going to be faults. So this is a process that takes less than 5 minutes, because unlike the typical processes where you have to go and digitize strings, I simply extracted more of point clouds from the seismic data and constructed a mine scale deposit 3D automated geological model. The other one that we do, which we have been doing a lot, it's more of pothole modeling. This work was started by Lebo Sehule, who was working more on the seismic data. And we just took her data set and we put it into a number of classification algorithms, and we're able to predict the number of potholes in the bushveld complex by using things such as the sidewall angle of the pothole, the diameter of the pothole, and also to use some of the reef characteristics to see how much changes are incurred in the channel itself or in the reef horizon itself. The other thing that we do is in situ prediction. So what you're looking at here is a bunch of elements of geological observations from channel width going to the gold grade itself. And we do more of future correlation heat map that you're looking at here. And we're looking at things that are correlating more. And for the purpose of illustration, I will simplify this to a typical simple decision tree where we take features based on their importances and we use them for the prediction of gold. So more in visualization of it in a tree format, you're going to see the diagram that you see on the left-hand side, on the right-hand side. But in the coding format or in the logic form, it's actually a nested if statements. If you have ever worked with if statements, so a decision tree is actually a simple nested if statements where we say if the fraction of the conglomerate is a particular value and the channel width is going to be of a particular value, we can use this to predict the gold grade. And we can also use a combination of different variables. And the output of this was to compare whether there is any spatial relationship between the channel width in this case and the conglomerate fraction. And we can use this to come and actually do the prediction of the gold by using a simple decision tree. And what you are looking at here, each and every color on the left-hand side represent a particular region that has a particular value that can actually help us to predict the gold on the right-hand side. The other one that we have done, as I have told you, I also work a lot with artificial neural networks and random forests and so forth. So I think if you can master how to use a decision tree, you need to do that before you can even move to a random forest, because you may get lost in a forest if you don't understand the tree on its own. And what we have done here was also to take a bunch of elements from an iron ore, and we managed to do a model testing on the left-hand side using a number of algorithms. And on the right-hand side was when we tested the model, and it predicted quite well because this was an assembly-based method. We plotted a table here, which showed us that artificial neural networks performed far much better compared to any other model in this particular data set. So we could predict iron ore from simple observations up to 98% accuracy in this regard without even having iron ore assays or ion assays. Then the last one is mainly automated rock classification. I also do a lot of things where we have geochemical data or geological observations. And from this, what I simply do is to come up with some sort of distributions of this. I also run multiple algorithms to check which rock types we're dealing with. And you can see in this case, this is a confusion matrix in practice. You can see with this particular model, we managed to predict almost each and every one of these iron or rock types, except for few, 2 to 5 that we didn't get. And in the end, I can do a whole mine correlation of the boreholes that are there, again, using the same form of classification. So it means when I log core, I don't have to record many things. I just need to record the observations on what color do they look like, what sort of grain size, and feed it into the algorithm, and it will tell me what sort of rock types do I have. To conclude, because this actually can take the whole day if I want to continue, just keep in mind that fundamentals of modeling remains, including in machine learning. So models are created for specific goals. You can't say you want to create a machine learning model without knowing what to do, and their accuracy depends on your input variables and the expertise of the modeler. So this is key why you need your geology skill. You don't need the data scientist to come and model your data. The second one is that avoid modeling for comfort. Many times you get called to say that we want you to create a model and we want you to compare it with our existing model because we believe that our model is going to be right. And that is more of modeling for comfort, because you're actually using machine learning to confirm decision already made or partially made. And this can be very dangerous, because if the outcome of the model differs with what you anticipated, you tend to think that machine learning is wrong just to defend what you're doing. So avoid fixing your mind when you do geological models. Other one is that you need to spend more time pre-processing your data, training models and testing models for future deployment. You cannot just rely on one particular model, especially when the data changes. And then the last one, ensure that you optimize the performance of models before you even do the actual estimation itself. And with this, I just want to conclude and thank everyone for joining us today.
Thank you very much, Glenn. That was extremely informative and very interesting. A couple of questions in the chat box. One from Carrie. how do you correctly differentiate between a false positive and a true positive?
So that is actually quite easy if you are dealing with labeled data. So for an example, before you do the prediction or deploying the model, it means, let's look for an example. I want to predict the magnitude of a fault throw of some kind, to say that the movement is about 40% or is 40 meters or 100 meters and so forth. So it means firstly, I'll be having data set that will be having these labels. And what I do when I'm training the model, I want to ensure that the outcomes of the training models match the input data sets. So if they don't match it, those are going to be false. And if they match it, those are going to be right. And actually the false positive is when all the characteristics are actually similar to what you anticipated to get as an outcome, but you are getting a number that is not related to your expected value or your labeled value. In unlabeled type of a data, this is slightly difficult because in unlabeled forms of a data, the problem tends to be multidimensional. You can still calculate using what we call the Gini index. And the Gini index actually tells you how far off are you from the input variables as a combination, not just one particular individual feature. And that also is a quantifiable measure.
Thank you. Michael, you have your hand up.
Yes, well, thanks very much, Glenn, for that awesome presentation. I'm sure you know that I'm a big fan of Python and machine learning, and definitely want to learn a lot more about it going forward. But I really just wanted to find out, have you ever been considering coming up with a course or demonstration for other people that are very interested? I'm sure that there are a lot of people out there that want to learn more formally about this. Thanks.
So I have put together a course which I taught this year to a group of people from Sweden. Earlier this year, it was more of a master's 2 weeks type of a program, and I have just completed designing more of a 3 to 5 days workshop-based exercises that people can do. The only thing that needs to be decided now is whether we're going to run this using the GSSA or we're going to be running this using the VET's facilities. So yes, I have considered this because I have received a number of emails, including from companies. It's just more of the platform that will be more easier for many people to join on a 3 days workshop where we also do hands-on exercises.
That sounds great. I was actually going to come and chat to you about that, but we'll take that offline. There was guys, we've got Glenn's contacts. It should be, Glenn, could you just show your slide with your email address?
Sure,
please?
Not a problem. I'll do it just now.
Or just stick it in the chat. That'll make it easier.
Ah, I see.
Okay, there it is. Okay, so there's Glenn's contacts, but we will certainly be talking to him, and in one way or another, there will be some more information on this, either through VITS or through the GSSA or elsewhere. We now move on to our next presenter, Maria. Maria, would you like to share your screen while we introduce you, please? Okay. Maria is from CSA Global, and she's going to be talking to us about database management. We can see you, and if you'll unmute yourself, you are unmuted, off you go. Thanks, Maria.
Excellent. Thank you for those that have only seen my picture. This is me, so that you can put a face to the voice. Okay, so my name is Maria. I started as a production and exploration geologist with mining.
Maria, we've lost your volume.
Oh my.
You can get closer to the microphone, please.
Is this better?
A little, but if you can come any closer.
Oh, okay, just a second. And now?
That's much better.
Okay, so there we go. So hi, my name is Maria. I started with production and exploration geologist with a mining house. I hold an MSc and A+, an N+ and SQL qualification, and recently added to this with a compliance management qualification. So currently I work as a consultant for CSA Global. At CSA Global, we do.
Maria, you're getting very quiet again.
Just a second. I'm just going to unshare quickly and then just check my settings. Just a second.
Okay.
Okay, is this better?
Yeah. Okay. Right. Okay. Bye.
Sorry, Tanya, is this better?
If you can do a little bit louder, that would be even better.
Oh my, because I'm now literally shouting into my mic.
That sounds a little bit better.
Okay.
If everybody else just put your volume up higher, that's the best we can do.
Okay, so at CSA Global, we do a diversity of services across the life of mine, from corporate reviews all the way through to mining and development studies, resources, water and technological data. But today we are going to talk about data management and database management. So when we start our career as geologists, we don't always realize what happens to the data that we collect. So today I'll be giving you a quick tour of why data management is important and what your role in this process is. What happens to your data once it is ingested, how it is stored, the broad overview of the back end of a DBMS, and now that it's stored, now what? So what do we do with the data after that? So let's start. Why is data management important? During the entire life of mine or the project, the decisions are based on the data available. So by ensuring that the project has an early implementation of data management best practices, increases data integrity and security, allowing for information decisions to be ultimately adding value to the project. Which then means that if you have poor data management, it increases the risk of the project and it lowers the confidence in the data, and so lowering the asset value. So when you do present your data, you have to know that it is trustworthy, so it's auditable, a true reflection of the area, so it's validated and you can take it to the bank, quite literally, as part of any feasibility study. As a geologist, you will be collecting large volumes of data, as has become evident from all of the previous discussions that were hosted today. You can see you can collect all different types of data, from geological, geotechnical, hydrological, soil, sample, assay, or any other related data for the project. And if it is collected and stored correctly, the data will help you to increase the project's value. So this is a process flow depicting at which point data will be collected on a specific project.
as data gets captured, it gets imported into the database. So in this case, you'll see as we move along from where it's drilled, the core goes to the core yard, it's loaded to the tables. Once you start looking at the core, capturing photographs, capturing your logging, your sampling, your geotechnical density, or any other related data will get captured along every single point. And then once it is captured, it will then be put into a single source for your data. So as the data collection begins, the data management process also starts. The input form or front end will already be set up in such a way to ensure that the data conforms to prerequisite parameters of the data set. So data collection can happen either in an Excel template, or you can have already suited captured solutions such as Acquire or GeoBank or Logcheap or Sable. So once it is captured, it needs to go somewhere. So we have traditional geological database solutions such as Datamine, Datashed, Acquire, and then we've got newer generation solutions such as MX Deposits or Core Plan or Core Track. These newer generation solutions actually uses software as a service on a cloud-based platform. But this brings a new slant to the entire data governance and security that one must be cognizant of as well. So in a digitally mature environment, all of the different databases will form part of this IDMS, which is an integrated data management solution, which will then allow for a company or project to have a single source of point of truth. You'll have QA/QC control and reporting. Your database will integrate with mining software. You'll have real-time or near real-time analytics and reporting. And with that, you'll have a robust security and disaster recovery system. So what does it mean and how does it work? So now that we know where the data comes from and the path it follows, what does actually happen? So in the more traditional geological database systems, you'll have a relational database that's based normally on SQL or simple query language, which basically means that your SQL backend will connect to a front end. And once you have your data in your SQL backend, it will be set up with constraints and relationship keys that will allow certain values and certain denominators to go into specific tables. So that means the tables will be created on certain characteristics. So you'll have, for instance, library tables that will have specific data for the project. So your lookup, so that would specifically speak to the type of geological data or mineralogy or the commodity that you're looking at. And then secondly, you'll have downhole data. So that would be any data that you have captured as you were logging the core. For instance, did you encounter a fault? Was there a fissure? Was there any extra mineralization? And then you also get point data. So that would be if you are doing, for instance, sampling of water, and you'll get line data. So if you are doing a sampling in a trench, and then you will get system data that will be preset up with, for instance, coordinates, and you will pre-program your database with that. So once we have that data in the database, we'll have to look at it in terms of validation as well, because now we have that data. So can we trust the data and what can we do with the data? So in terms of validation, firstly, we'll look at completeness. So in terms of your reporting codes, there are certain sets of data that you need to certain parameters in the data that you have to look at and have validated in your database. So you must have coordinate systems and you must have actual coordinates. So you have to look at your data set and say, well, do I have firstly all of the data that's needed to look at this in terms of JORC or SAMESC or NI 43101? And when I do have the data, sorry, this is really doing what it wants to do at this point. So do I have all of the data that's needed to give effective reporting? And when I look at the data, do I know that I have all of the sampling data that is needed and that we have no overlapping samples, that we have no samples that have been reassayed, but we didn't consider the new data values that were given? And also, did we look at locations and descriptions and units and so forth? Are all of that really trustworthy and complete? Then secondly, once we look at our assay data, we have to say, in terms of our resource classification, can we trust this data? So we must provide assurance that the data underlying our resource model is accurate and it's truly a reflection of what's going on in the ore body. So to define these uncertainties associated with sampling and sample preparation and analysis. So when we look at our CRMs or standards, when we look at it, we say, okay, we have this sample standard and we have an expected value. And we will say the sample fails when it's more or less than 2 standard deviations. So therefore, this sample, this standard has competed well within this time frame because it's consistently passing and there is no drift or bias. Unlike this CRM, where we can see even though it's passing, there's a continuous negative bias when the laboratory is reporting on the values for this sample. In terms of this CRM, we can see that there are 2 distinct populations when looking at the CRM. We can see there is a positive drift or bias and a negative drift or bias. So as part of your data management, you will have to look at your QC plan and consistently look at evaluating how your standards and your assays are doing in terms of your expected results in context with your ore body. So this is important because this will underpin the confidence in the data that will dictate the classification of your mineral reserves. So basically, now that we have established the confidence in the data, and the mineral resource team can take what we use here and we say, okay, so we have excellent data management, we trust the data, it's auditable and it's a true reflection. They can use the data to classify whether it's a reserve or resource, and that will then underpin your block modeling or your model of your mine and your life of mine or your mine design plan, which will be used to tie down investment opportunities going forward. It used to be said that the world's most valuable resource was oil, but no longer is that the case. The world's most valuable resource is now data, and that data must be true, auditable, and an actual reflection of what's going on. And it's imperative to know that whatever you do today in terms of your core log will live on forever. It will be forming a part of any life of mine or project that you are currently working on. And a good data management principles will underpin excellent results for a project, which will then add value. So if you have any questions or comments, now would be the time to raise them. Sorry, the technical glitches were a bit disconcerting. So Any questions or comments?
Do we have any questions for Maria? There's a question from Andrea. How similar is Sable to Acquire?
Okay, so can you hear me better now? Okay, so basically, the main thing, I'm just going to unshare quickly and see if I can sort this out because it's really frustrating. Is that better? No, still not. Okay. So basically, the main thing with most geological databases is that they're all in SQL. And then what happens is it's the perceived idea of what you want to share or capture. So it would be, for instance, if you are looking at more geotechnical data, it will definitely be worth your while to look at Sable. Where it comes to Acquire, it's they've got a very nice complete suite of options, and they're focused entirely on extra information pieces that one can add more to your production database as well. So it all depends on what it is that you want to capture. Sable is very adequate. However, it tends to be more focused on geotech and more specifically for the house mining industry that it has been designed for previously.
Any other questions?
So I'm quite passionate about data, and I'm really sorry that the technical problems has hampered a little bit. But if you have any questions related to data management, because a lot of times it's not so sexy, and everybody when they start, they just want to look at the core or go exploring and trapezing around, mapping the environment, looking at everything. And basically what happens is you tend to forget that down the line, your name gets stuck to that data that you're collecting. So starting off with good data management principles when you are starting off is an imperative, because it lays the foundation, as you heard from all of your speakers before me. It lays the foundation for if you want to do machine learning. One of the things that was mentioned was, do you have clean data? Do you have enough data? With your discussion on SGS this morning, it was like your assay data. So do you have data that you can trust? So it is imperative that when you look at data management, you shouldn't think of it as the next person's problem. You should always think of it as, where do I start in terms of my foundation when I grow as a geologist and I look at data later? Do I want good data? Do I want reliable data? And already start doing your part now. And then I see there is a question in terms of a big price difference. Okay, so yes, with all of your data management software, there is a definite price difference. Acquire tends to be on the more expensive side to some of the other solutions, and then your MaxGeo tends to be a bit more reasonably priced, followed by GeoBank, then Sable, then I would say Datamine Fusion, and then, as I said, on the higher end, it would be Acquire. So yes, I see Vickers asks here, would I suggest that Geos has some SQL knowledge? Absolutely. When you start looking at data, even if you work with your database manager, if you have an idea of what you want to look at or the way that your database administrator needs to extract your data for you, it is always good to understand what the logic is behind the scenes. So how does SQL read my logic for my data so that you can know exactly how you can look at the data. So yes, definitely some SQL knowledge will go a long way in your career.
Thank you very much, Maria. Any last question? Going once, going twice. Sold. Maria, thank you ever so much for your presentation. We'll definitely call on you again to talk to us more about this. If you'll unshare your presentation, please.
Sorry, Tanya, I see they snuck one in. I will answer the question in the chat. I will be available for some more questions to answer in the chat. And thank you very much for the opportunity. I'm really sorry about the technical glitches.
Technical glitches are part of the course on an online presentation. What we can do about that.
Okay, cool. Thank you very much.
Thanks, Maria. Okay, Matthijs, if you wouldn't mind sharing your screen, please.
Anna, thank you. Hello, everyone. Let me just quickly share that.
Okay, and while you're doing that, we've got Professor Matthijs Dippenaar from University of Pretoria, who's going to talk to us about engineering geology and hydrogeology or geohydrology, depending upon which way around you like it.
There's no question it's hydrogeology. The world. Okay, wrong side around, share screen. Have I shared my screen yet? No, not yet.
No, not yet.
Let me just quickly get the right one. There we go. Okay, so hello everyone. Thank you for the kind introduction. Let me just plug this in. So I'm Matthijs Dippenaar, and as Tanya said, I'm an engineering geologist and a hydrogeologist at the University of Pretoria. And I present the undergrad and the postgrad parts of these courses at various parts in the year. I just want to see if I can maybe just quickly show you my face. I don't know if you want it on or off, but just so that you can at least meet me quickly. Okay, so apart from that, I can now get rid of that. So in geology, we start, as most of you are aware, and you've probably heard a lot of it, by what is geology, and mostly we work there with the history of the planet and stuff like that. But as all sciences basically work, we changed over time the focus points of the sciences to become more applied in different places where there are different needs for this. So in engineering geology and hydrogeology, we look beyond, for instance, geological resources. And if you think of geological resources, we are mostly focused around those on the left-hand side. Minerals like metals, coal, gemstones. But we also look at fossils, for instance, as a geological resource, and we look at construction materials. So when we start to look wider than just the classical sort of mining, we realize that all substances below our feet comprise geological resources. So we look at that then also in terms of construction materials like clays or dimension stones or crusher rocks and all of those things we use in construction. And then also things like water, especially groundwater, because that's in the subsurface. So it starts from there, it interacts from there, and all of those things then contribute to the bigger use of geological resources. I'm going to switch on my video. I think I like having it on, if you don't mind. And soil, okay, then obviously also soil. Even though other people are better at interpreting what soils are used for, it is still a geological resource. So we look then specifically in the broader fields of engineering geology and hydrogeology at rock, soil, or water, how it's distributed, how we can use it, how it behaves, and then also risks posed by them and how we can protect them. Okay, so just a quick introduction. I like this little picture. It just shows you some idea of some broader geological careers. And in here you can see we can overlap between so many different geological professions or uses of the broader theme of geology. So as geologists, there are so many ways in which we can work in different professions. And today, the few slides I have, mostly pictures, because pictures say more, and then I don't read slides, then I'm forced to look you in the eyes and talk to you. But just show you an idea of what we do in general. So engineering geology and hydrogeology are two different professions. We at the University of Pretoria work very closely on the overlap between them. So I always like to start with some version of this picture to now think what one would see. Do you see a road or a bridge or traffic that shouldn't be that quiet? And then you start to think beyond that, what this can tell you in different professions. An engineer, for instance, might see the design or the road pavement layers. But what do we see? That everything is built either on or with or in geological materials. We're not floating around in space. So we're making cuttings, we're making slopes, we're founding stuff, so we're creating more stable platforms, and we're using materials to make them work. So if you just look at that bridge, the cement, the aggregate, everything in there, even the steel reinforcement are products of something that was mined. Okay, but construction materials. Okay, so we think a bit further about geological materials more in terms of functional application. So in engineering practice, we think of it about how we position and design engineering work. So we work very closely with engineers, mining engineers when it's about slopes, for instance, and then very often civil engineers. Functionally, we look at the strength, durability, deformation, and permeability of materials, because those are the very fundamental design requirements. So here we start with the pictures, obviously dams, a very good example. And I just placed them not necessarily in very strong context to follow on each other, but dams, why do we build dams? We build them because we need to store water. We build them because we need to control floods. They are for power generation. So there's an enormous amount of reasons why we build dams. It's not just water reservoirs. So what's the problems here, for instance? The foundation of the dam wall, it's an extremely heavy load with only water on one side. So in other words, its interaction, its forces are very complex to understand. And founding a dam implies that it leaks under it. So we need to understand the flow under the dam wall, because remember, it's not an inevitably deep structure that's impermeable. So this is the example of the De Hoop Dam near Steelpoort. And we look at the foundation and materials, and very importantly, the structural geology. If you're building on faults or contacts, it makes the foundation conditions differ between different parts of the foundation, and it can also cause it to leak, for instance. The Tukela Dam scheme near Harrismith, another nice example, very deep excavations. Hydrogeology, they needed to think of that. This was for electricity as well. Some of the materials from the dam quarrying could be used in the construction of the dam wall itself. So in other words, in an area such as this, they could really, really use a lot of the materials. And that's obviously a sensible way to use the material you get out of there. You still need to apply to use that material, but So dams, an enormously big part of South African skills, a lot of good dam engineers here. And you all know our climate, so if not using other means like groundwater or desalination, then surface storage of water becomes necessary. Large parts also of South Africa bring water up hundreds of meters to the skim to eventually get to the Vaal Dam to supply water from there. So a lot of transport and a lot of construction of surface storage features for water. So this is deep construction along, it's a station. They needed there at the bottom to remove a lot of water, fairly expansive yellow clay. So for transport corridors, but also with urbanization, the idea is to become less peripheral and to become more vertical. So you would want to build cities higher and deeper in the middle so as to primarily, obviously, use space better, but also to reduce movement over very large distances. And then secondly, more maybe a personal opinion, to just keep green space around cities. You sometimes just stop progressively growing and growing until the entire place is built up. So deeper and higher developments become harder work. So you now need to start to remove water. You need to start founding deeper. And you can see on this picture a lot of reinforcement to maintain the structure and the excavation's integrity and to withstand, for instance, the swell of those clays next to that. This is also part of the Gautrain for the piers. Here they drilled a lot of holes because it's dolomite, remember, there in that area. So all underground cavities had to be, for instance, had to be completely filled up so that you could be very, very certain that those footings or the viaduct don't collapse. So between the footings, you are fairly safe, but at those points, all potential sinkhole risk needed to be completely stopped or prevented. And this also for transport, same reason, densification, urbanization, and providing better opportunities for transfer and transport. Obviously, the flyover had a lot of potential in terms of being safer between, so you could actually properly investigate the dolomite section there. So dolomite's problem subsidence, so any vertical volume change we get in these areas due to various reasons, but also the construction materials, the loads, and then the grouting and stuff that needed to stabilize it and needing to get rid of water. So the people who worked on this really spent a lot of effort and skill on getting this right. Bridges, this is the Msikaba Bridge on the N2 to basically get you between the Eastern Cape and KwaZulu-Natal. It's one of these bridges are world-class bridges, very important foundations, construction materials. Once again, the people working here are putting in an enormous amount of effort and skill to properly characterize this rock, the mechanics of this rock and the hydrogeology to get it to get the moisture conditions correct. There are more than one of these bridges, and obviously the road itself. So once again, it is access and corridors to move between different places. So access, but yes, beautiful bridges that will one day be finished, and then you will be able to access that portion with much less time. Roads in general, so for access and different transport corridors. So here's just a few smaller scale pictures of a road in Wynberg where they, for instance, had to use geotextiles between a fairly expansive, if I'm correct, bedrock or residual soil or below that. So they had to use various means of stabilizing. But just in general, if you look here, bottom at Gariep, the influence of a slaking mud rock next to a very resistant dolerite And if you now just think if with this road being built through there and the cutting on the sides and the use of the materials in the deeper road layers, those properties will be extremely different. So in other words, you have the engineers have to design this, but based on the geotechnical data that the engineering geologist does, sampling the correct material, conducting the correct tests. Bottom right, different road layers. So few people realize that it's also in geological work that we identify properties for materials that can progressively build up to the upper layers of a road into a better quality material for that purpose. So once again, working very close with engineers in getting the correct materials, and then they design the road. And then upper picture transport, using some of the cut material on the side. You can actually use some of that material in the road by having a cutting and then using those materials in the road as well. Dimension stone. So these are just a bunch of things that we look at. The Durban Hilton on the bottom, the Swartruggens Church, you can see probably 4 or 5 different actual rock types in there. And then one of my favorite pictures always, the city airports or malls, where they have this nice variety of rock that they use for cladding. So apart from just using rock and gravels for actual fine material like sand and aggregate in, for instance, concrete, you can also use them as cladding stones. Very popular, and it makes good building material, many of them. Going into a bit of risk assessment, this is a sinkhole in Littleton. Sinkholes form either due to downward ingress of water or because groundwater is lowered substantially. It's an enormous problem. And mostly in South Africa, it happens because things like gutters or underground pipes or sprinklers leak over time, or runoff is discharged onto one point and the dolomite under it already has cavities or weak residual dolomite. And then in that process, as that water enters, it just adds weight and it has already a depth, very likely a receptacle or a cavity, and you have this erosion of everything above it into a cavity, which is either under you or just offset. These are terrible issues when you get to insurance claims, for instance, because these are really, really risky areas and conditions. So in our current guidelines and regulations, you have to identify these in a very specific way by doing a dolomite stability analysis. So in these areas, the rules are quite different to normal housing and normal urban development. But South Africa is quite well prepared for that because in Gauteng, it's an enormous part of the population of Gauteng stay on dolomite. So the risk assessment becomes a very much more important. It works on other limestones too, but once again, the dolomites in Gauteng, they are specifically troublesome simply because of the development there and how they weather in that climate and on that elevation. So many reasons why the dolomites work a bit differently here. Cemetery on the left in Irene, bottom right in Babsfontein, 2 different types of sinkholes. Top left one due to leaking irrigation from the top, and the right one, I believe, was over abstraction. But the point remains is these things lose a lot of volume of earth material, do a lot of damage to infrastructure. So subsequently, it becomes really, really hard to start to remediate these things and to try to solve them and to fix them completely. Slope stabilities, steel, drainage, just these things. As engineering geologists, we have to quantify the parameters and the information required to fix these. So different methods, once again, the engineers do it, but as geologists, we characterize the properties of the soils or the rocks in soils by getting the parameters that will affect the shear strength of the soil, and with rock, the discontinuity data, or the very much like structural geology, the interaction between different sets of joints or fractures or beds in a rock mass. A very good description of the materials so that you can start to infer the behavior. Okay, so that's now quick on the engineering geology. And you'll check my time, but hydrogeology, next one. But people seem to forget that groundwater really is terrestrially the most prominent source of fresh water. It's now easy for some people to see desalinized, but the energy and the transport, there are just so many costs related to desalinization. So fresh water is obviously in the general perception the best option, because you can see it and you have this impression that you can contain it. But at anything between 10 and 100% or times more, groundwater occurs on average in the world, really much more abundant. Fresh water is scarce and scarce. Groundwater is also very poorly and widely and randomly distributed. But if you just look at a map of any country like South Africa, you'll see the rivers do the same. So in hydrogeology, we look at the occurrence and distribution of the quantity of water underground, as well as its quality, so keeping it clean, how easy or adequately we can use it for something, and then this whole sustainability and reciprocity, a bad word, I can't pronounce everything, between humanity and biodiversity. So in other words, it's really important in the water cycle. So nice example of that. And progressively over time, you might look now, if you look at old books, this underground part has really developed with much more detail into how water moves in the subsurface. It used to just be infiltration or base flow, and nowadays it's much more detailed. So just some other pictures of Cape Town, of how simplified their water interaction works. And the bottom right, just some examples of springs. So a spring is anywhere where the groundwater table intersects or daylights on the surface. So in other words, groundwater is really a very big part of the water cycle. And hydrogeologists nowadays work bigger and bigger, because the part the groundwater system has in the water cycle, it seems that everyone is now realizing, simply by its sheer volume and the absolutely wide distances that it can move over time, that it is really important to start looking at these different aspects together rather than in isolation. So it's key or core in the principles of sustainability, because it's basic human right. So in other words, its cost is fairly low. Its availability is problematic, which implies that in an environmental context, it's higher risk to work with water and groundwater. So in other words, groundwater falls a bit stronger into the environmental management governance principles, because we look at that not solely from use and risk, but actually from environmental conservation and equity. Yes, it's there in engineering geology and any geology, but we start there when we get into water. So springs and water supply, left is Oranjezicht or the Ou Stadsfontein in Cape Town. Right-hand side, Grootfontein, it's next to Rietvlei Nature Reserve. And in the middle, the lower fountain in Groenkloof Nature Reserve. That little house in the middle, that's the old pump house. It used to be coal-fired, so the actual spring is there in that little small concrete structure on the left-hand side of that middle photo. So we protect these springs with collection chambers, mostly to keep the algae from blooming and just general pollution. But so water supply, a very big part of hydrogeology. The springs are nice examples, but obviously the same happens through actual drilling and supply from proper boreholes. Okay. So when we drill for boreholes for water supply, we site them usually with geophysics. And when we do that, it means we are looking for lithologies, which might have a different electromagnetic behavior. When we look in dolomites, we sometimes use gravity because you can detect cavities and waterfall density changes and differences. So no little sticks. We use geophysics. We use remote sensing. We use just proper field mapping to identify contacts and structures. And then groundwater hydrogeologists will then be involved as well in designing the actual depth at which you want to install your pump, for instance, because we can, with our pumping test, get an idea of the depth of the fractured networks or put cameras down boreholes. We also work in protection zoning to protect greater water resources. So this, for instance, still at Groencliff or at Fountains Valley, but we do tend to generate larger areas of lesser, like buffer zones, like you would with a wetland, to protect also well fields or boreholes that supply water. We construct our boreholes to reduce pollution into them. So a lot of design goes into boreholes and water supply from groundwater, but groundwater is no longer only about water supply. So we use them also as monitoring wells in larger areas to just detect if pollution would occur, or if just things change, if water quality or water quantity is substantially changing for some reason. So in other words, it's also used to monitor the relationship in the greater water cycle as a sampling point, because it's a lot of interaction between our groundwater system, our soil water system, our surface water system, and the atmosphere in general. Also, all these things are groundwater dependent ecosystems if they sustain the reasonable biology and where water comes out the wetlands. So in other words, groundwater input contributes to, for instance, the legal aspects of wetland delineation, and it works interactively with hydropedology, for instance, and hydrology. So it's just a very important link. So impacts, pollution, over-abstraction, injection, there are so many things that affect water, and water affects infrastructure and disturbance and overuse and quality. So in other words, there's a very, very big interaction between water and any development. And as a consequence nowadays, and it's no longer just supply. One has to now monitor the quality and the quantity changes because of certain land uses, because it goes elsewhere. So just some examples of, for instance, landfills, mine water, petroleum, effluent, cemetery, sanitation, fertilizers, dewatering, irrigation, all of those things have an effect. So picture time, contaminated fill in Johannesburg, just some corrosive material coming out there because it's a fairly industrial area. And then you get these things starting to precipitate. It's corrosive to the concrete, or actually the cement in the concrete. And obviously it reaches proximate water features, but with that quality, it also starts to affect the integrity of the steel and the cement in that concrete. So in other words, it starts to have a secondary effect, which is not a flux, which is not a flow. On the right-hand side, shallow burials and pit latrines. This comes from Taung. Obviously, climatically, different things have different influences. It just proves the point that we also have these dispersed, spread out sources of contaminants that are releasing different kinds of contamination over larger spaces. Issues like this with pit latrines and burials, for instance, are more microbial. So in other words, bugs. So you tend, and just general sanitary issues. So that goes very often into boreholes, because the water supply boreholes might be close by, or even to streams. And then you get those pathogens reaching that and you get sick. So then disease becomes a problem. So diarrhea or E. coli or something like that. So it does affect the flow and the movement of water, but mostly it affects the quality of the water. AMD, most of you have heard of it. Bottom left, there seems to be steam coming out of there, so some combustion underground. And you can see that shape there is the edges of underground collapse, daylighting on the surface. So a mine-related sinkhole with smoke coming out and AMD. And at the bottom, just really, really iron-enriched water. So these things are geotechnical, environmental, and hydrogeological issues. But the smart hydrogeologists in geochemistry, a lot of people work almost exclusively in mine water. They have to solve these issues. So it's a lot of sampling, fieldwork, monitoring to find a solution. Holly City, Krugersdorp, just showing basically the same AMD and water quality issues. Many of these mines and quarries and open pits also, of course, have to dewater and lower the water tables very, very substantially. And then you have the tailings and the dumps, and then just releasing this bad water quality. And this goes on in poorly rehabilitated situations where this just never gets solved. So in other words, just in mining, as with waste, as with sanitation, all of those, just getting dirtier. Petroleums, I'm going here. So pollution from non-aqueous phase liquid, so it's petrol spools. These move differently. They release vapors, and that obviously poses different problems because you have different viscosity and fluidity fluid and different gases coming out. So things like this make it very much harder. So to just end off the groundwater, you can have all these techniques like modeling where you now start to infer regionally and then taper in how water moves and how everything affects that movement. We create hydrostratigraphical and conceptual models to understand the influence of aquifers in context of unsaturated portions or low permeability portions. So modeling is almost is a career on its own, and it is used as a very, very important tool to understand groundwater movement and quality. So just quickly closing thoughts. You spend a lot of time in the field acquiring data. It's really a nice field trip. So you do need to like geology. You need to understand geology. You can understand quite a lot by understanding flow hydraulics. But if you understand the geology in hydrogeology and in engineering geology, you really, really understand how to start to plan what's going to happen when you have this idea already of what to expect and what to work. So geology is really needed. You need to understand the other sciences like maths, physics, chemistry, because it remains a proper science. And in that, we understand the geology better because we can understand the mechanics of failure. We can understand the calculus behind flow equations. We can understand the redox chemistry of corrosivity or of contaminant transport. So that's really important. And as with all sciences, your product is your word. So how well you write it, how well you say it. So you must learn, like I tell the first years, if you continuously misspell asthenosphere, it's not a phonetic mistake, it's that you don't get the word right. So you haven't learned it, and that's how you should work. You should get everything right, because you will tend up here to work more in a consulting environment where it's about conciseness, about never giving more than what you are what your contract makes you liable for. So all of this, and then just nice additional work that some people do with additional computer modeling. So just some pictures, second last slide, actually. So a lot of nice fun outside days, just some random examples. Rules are getting stricter. Some people are less keen for the fieldwork nowadays, others like it more, but someone needs to acquire the data. And it's just really, really a very nice job. So join the club. There's the professional societies. You all know GSSAs, so that's why I didn't put them there. These societies facilitate the process for professional registration. The academics talk to them a lot, and otherwise just go there for interest sake to see what they do, what we do. We're all a part of that. And because it's just really, really, really fun and a good job. Thank you. I kept you for just over half an hour. Thank you. I don't know. You must not tell me if there's any questions or something. I will have Tanya take charge of that.
Thank you very much, Matthijs. It's strange having you present from an office. We're used to seeing you out in the field. There are a couple of questions in the box. The first one, and Paul wants to know, with respect to engineering geology, which software would you recommend for slope stability analysis?
Okay, so I don't model, and I'm not really a rock mechanicist, but there are hordes of packages. We use the Rockwork set, but you can really, in my opinion, I've heard few bad things. People pick it like in groundwater models, if people just pick feed flow or whatever they like. So I'm not a modeler, so pick a model.
What are the most important things to consider when compiling hydrogeological reports for water license applications?
Okay, so in that, the nice part is we do usually the hydrogeological investigation and then send it to someone else for the water use license application. But there are quite good guidelines of what your report should entail. But all in all, it will depend on the use. If it's for supply, they will need you to provide the information required to see whether the catchment can sustain that additional abstraction. If it's for quality, then you will need to come with proper baseline data and a means of monitoring that. So it's probably very dependent on your license, the specific license, and the magnitude of it. Is it for your single house or are you watering a mine? But the point is you have to mention pretty much everything: recharge, S values, T values, qualities, and if you don't have something, you should be able to motivate why you don't do it.
Then there's a question from Carrie. Mines dedicate significant resources to understanding and working toward responsible interactions with the natural environment. The same level of consideration from development in cities, either through engineering geology or civil engineering, is not readily visible. Could you comment on legislation or regulation or policy regarding protecting water quality or preserving water resources in urban and peri-urban areas?
Compliance. Mines have one owner and they want to do it. In cities, there are 4 million people, everyone with their own reason to not do it. The legislation's perfect. The process is perfect. I think it's just too many fingers in the pie in cities. Bad answer, but a good answer.
Yes. How would someone, a student, transition into engineering geology to focus on infrastructure or construction solutions from our field of expertise as geologists? Are there firms or companies out there that you might look to for possible exposure in this career path?
You can certainly, I know Rory-san, you can certainly get there, but it doesn't work that well, because if you now think how the professional registration system works, it's the same everywhere. So you need a year 1, 2, 3, 4 build up to a professional qualification. So all in all, you can work in there with experience and then later register based on your vocational history, but it's a separate application. But it works very much the same as any other field of practice. Sadly, the transition often comes too late. So you theoretically should study it, or just in a company be exposed to it to the point so far that you can eventually require a prior learning application for professional registration.
And then Marty has a very interesting question. Why is it still a challenge to accurately find good underground water sources today, even with so much technology? The number of blanks are alarming. What, in your opinion, would help in limiting the chances of hitting a blank?
I think that question is the same as anything else. I think we are biased in groundwater because there is no requirement to validate a borehole that's cited by non-scientific methods. So in other words, everyone just thinks that this person cites boreholes. I don't believe we have many blanks. I believe in hydrogeology, we have an obligation that people don't understand, because you can get water literally anywhere. Any liquid that falls on the ground will go down. So in other words, water will come everywhere. Our obligation as hydrogeologists are to have a certain quality in a certain yield. So we design different things. So blanks, there are some. I would say the chance of success is very high. And I just think we hear all these stories, but there's a lot of people who cite and drill boreholes who shouldn't. And then they drill these 23-meter boreholes in abandoned iron formation instead of in the quartzite next to it. Real example, just because it's easier accessible. And, so I think there's a lot of things that aren't done scientifically, because in all of the conferences and stuff where we go, we actually see people present good and bad data. You realize it's really high quality, but you need a hydrogeologist, and you need a geophysicist, and you need the hydraulic testing. And so I really think we don't have many blanks. And I think if we have a 90% success rate, then it's excellent, because we prove it, we report it, and we don't lie about it. So Maite, I really think it's a challenge, but we're good at our job. So if you get people who should be doing the work, they get it right.
I think that's very much the point of Andrea's comment, that when the gift of the givers came to Grahamstown to drill boreholes for water 2 years ago, they used a guy with a divining rod rather than the geology department and hydro department at Rhodes University. And I've seen this in the diamond industry as well. They'd much rather hire somebody to walk around there with a stick rather than bring a professional in.
Exactly. Not all drillers are hydrogeologists. Some of them are, but not all drillers are. The point is, it's easy to do things if you aren't forced to comply by having been forced to become a professional registered scientist. If someone wants to just trust you, then it's your mistake. So he or that person has no real liability because you knew that. And all the information was available to tell you not to do that. So I don't know what we're going to do about that.
Do we have any other questions? Just put your hand up if you want. Otherwise, Matthijs, thank you so much again for giving us your time and your expertise, and we look forward to hearing from you again.
Thank you, Tanya. Always fun. Everyone enjoy it, and thanks for having me.
Thank you. Right, I'm just going to finally just share my screen. Because that brings us to the end of today's presentation. And so next week, we'll meet again, where we talk about what happens in various companies, large companies, small companies, consulting companies, the Council of Geoscience, and also in academia and research. And we look forward to hearing from people who are working in those industries, the advantages, the disadvantages, the exciting things, and the things to run away from. And so we look forward then to seeing you all again, same time, same place next week. Thank you all. Bye.
Okay, thank you, Tanya. Thank you, everyone.
Bye, Sanjay.